Hello there, and welcome to Science for Sleep, where curiosity gets cozy, space gets quiet, and even the most distant questions are allowed to take the scenic route toward rest. Tonight, we're going to follow a machine made by human hands, not for a few years, not for a few centuries, not even for the long, slow lifetime of our sun, but for a length of time so large that it almost stops sounding like time at all. We are going to ask where the James Webb Space Telescope might be in 1 trillion years. A trillion years? That is 1 million years. It is the kind of number that makes your calendar quietly close itself and refuse to participate. It is so far beyond birthdays, civilizations, languages, mountain ranges, oceans, and even the familiar night sky that the mind has to approach it gently, the way you might approach a sleeping cat that has not yet decided whether you are welcome. And yet, somewhere in that enormous question there is something very small and very human. Because James Webb is not a planet, not a star, not a natural moon that has drifted in gravity's care for billions of years. It is a telescope. A carefully folded, carefully launched, carefully unfolded observatory built from mirrors, shields, instruments, cables, fuel lines, bolts, software, and patience. It was made on Earth by people who ate breakfast, missed trains, answered emails, checked measurements, worried about delays, and probably at least once wondered where they had left their coffee. Then it was sent away from us, out beyond the moon to a quiet, gravitational neighbourhood where it could keep its golden mirror cold and watch the universe in infrared light. It is a strange thing to imagine, isn't it? A delicate observatory built for discovery, slowly becoming an object in deep time, no longer sending pictures, no longer waking up for commands, no longer turning its face toward newborn stars, but still somewhere out there, obeying gravity long after the voices that named it have gone silent. Before we drift too far, let me ask you gently, where are you listening from tonight? Are you near a window, with the sky hidden behind city lights, or somewhere quieter where a few stars are still visible? And what time is it where you are? Maybe it is late evening, and your room has that soft, almost silent feeling that comes after a long day. Maybe it's very early morning, and the world outside has not yet remembered to be busy. Or maybe you're in the middle of the afternoon, letting your mind wander for a while toward a telescope that is nowhere near your street, your town, or your ordinary sense of time. It is a fitting question for tonight, because Webb itself is a time machine of a sort, not in the science fiction way, with levers and sparks and someone shouting about paradoxes, but in the real astronomical way. It looks at light that has spent millions or billions of years crossing space. It sees galaxies as they were when the universe was young, and now we are going to turn that same idea around, not asking what Webb sees in the past, but what the future may do to Webb. If you find this kind of quiet cosmic wandering soothing, or if the thought of following an old telescope through the far future gives your mind a comfortable place to rest, I would be ever so grateful if you gave the video a like, maybe subscribed, and helped this little corner of calm reach someone else who might need a peaceful pause. No rush, of course. Buttons are patient things. They have waited this long. They can wait a few more seconds. And if you are already tucked in, warm enough, with your thoughts beginning to loosen at the edges, then you can simply let the question settle beside you. Where will James Webb be when almost everything it once knew has changed? To begin, we should picture Webb not as it appears in the photographs on Earth, folded into a rocket fairing or sparkling in an artist's impression, but as it is now in space. It is far beyond the moon, in the region around the Sun-Earth L2 point. That name L2 sounds almost too small for such an important place, like a label on a storage shelf, but it is one of the special balance regions produced by the combined gravity of the Sun and Earth. Webb does not sit exactly still there, because almost nothing in space really sits still. Instead, it moves in a broad halo orbit around that area, keeping the Sun, Earth and Moon on roughly the same side, so its vast sun shield can protect the cold instruments from heat and light. This is part of what makes Webb so good at what it does. It needs darkness, stability, and cold. It needs to hide from the warmth of the world that made it, like someone pulling a blanket over their head because the hallway light is on. From Earth, that distance is huge, about 1.5 million kilometers away, yet in cosmic terms it is still practically on our doorstep. Light itself crosses that distance in only a few seconds. If you could somehow stand beside Webb and look back, Earth would not look like a place with borders, roads, weather forecasts, and unread messages. It would be a bright world close to a brighter sun, the source of the gravity and sunlight that still hold Webb in its working rhythm. But Webb is not anchored there forever. The L2 region is useful, but it's not a permanent parking spot in the simple sense. A spacecraft there needs careful small adjustments, little firings of its thrusters to remain in the right kind of orbit. Without those corrections, the gentle pushes and pulls of gravity, sunlight and motion gradually nudge it away. Space can look empty, but it is full of bookkeeping. Every orbit has its costs, so when we ask where Webb will be in 1 trillion years, we are really asking a chain of quieter questions. How long will Webb keep working? What happens when its fuel is too low, or its systems grow old, or its instruments can no longer do science? What orbit will it drift into when no one is guiding it? Will it remain as one recognizable object, or will time, radiation, impacts, heat, cold, and chance slowly turn it into fragments? Will it stay near the sun's old remains, or will a passing star disturb it? Will the galaxy itself, changed by mergers and long ages, carry it into a completely different sky? These are not questions with neat answers, because the farther ahead we look, the more the future becomes sensitive to tiny details. If you try to predict where a leaf will float on a pond tomorrow, you may do fairly well. If you try to predict where that same leaf will be after a storm, 3 seasons, and a curious duck, confidence becomes a little less tidy. 1 trillion years is far beyond the designed lifetime of any spacecraft. It is far beyond the age of the universe as we know it today. The universe is not even 15 billion years old yet, and 1 trillion years is more than 70 times that. So this question is not about mission planning in the ordinary way. There will be no schedule saying year 1 trillion, check mirror alignment, download data, avoid cosmic dust. By then, if Webb still exists in any recognizable form, it will not be a telescope in the working sense. It will be a relic. A piece of human engineering carried forward into an era with no human engineers around to adjust it, polish it, praise it, or complain that the data pipeline is running slowly. That might sound lonely at first, but there is also something oddly comforting about it. Humans often build things for immediate reasons: a house for shelter, a road for travel, a telescope for observing. But once we release an object into space, it enters a story much longer than our intention. The Voyager spacecraft, for instance, are already leaving the Sun's neighbourhood, carrying little records of Earth into interstellar darkness. Webb is different. It was not sent outward to escape the solar system. It was sent to a working location near Earth to look outward while remaining part of the Sun's family. But even objects that stay close, in astronomical terms, can have futures that stretch far beyond their missions. A spacecraft does not stop being matter when its task ends. It becomes metal, glass, carbon composites, and dust-shielded memory, drifting through whatever gravity decides next. And gravity is patient. That may be one of the most important ideas for tonight. Gravity does not need anyone to be watching. It does not need batteries. It does not forget because a mission has ended. Long after Webb stops receiving commands, long after its transmitters fall silent, long after its sunshield is no longer a carefully maintained thermal barrier, but just a thin, aging structure in space, gravity will still be there, doing what it always does. The sun will pull, Earth will pull, the moon will pull, Jupiter, the great quiet bully of the solar system, will tug from far away. Passing comets, asteroids, dust grains, and the pressure of sunlight will add their tiny effects. None of these may seem dramatic in a single day, or even a single year. But deep time is very good at turning small effects into large outcomes. It is the universe's slow way of tidying up, except its idea of tidying is often to scatter things into new places. For the first years and decades, Webb belongs to astronomy. It opens its mirror toward targets chosen by scientists. It studies early galaxies, star-forming regions, exoplanet atmospheres, brown dwarfs, icy worlds, and the warm dust around stars. It does this because it was built to see infrared light, the stretched-out glow of cool objects and distant ancient galaxies whose light has been shifted by the expansion of space. But eventually the active part of its story will end. Maybe it will be because the fuel needed for station keeping and momentum management runs too low. Maybe a component will age. Maybe an instrument will degrade. Maybe some other practical limit will arrive, the way practical limits always do, even for machines that feel almost magical. There is no shame in that. A telescope that works for decades in deep space has already done something remarkable. The universe is not exactly a gentle workplace. It offers radiation, micrometeoroids, temperature extremes, and no repair shop with a cheerful sign in the window. Once Webb is no longer controlled, it will not simply freeze in place like an ornament hung on invisible string. It will begin to drift away from its carefully maintained halo path. The L2 region is not like a bowl where objects roll to the bottom and stay there. It is more like balancing on a very broad, very strange saddle. With guidance, Webb can remain near the useful path. Without guidance, small deviations grow. In time, it would likely leave the exact region where it once worked and move into an independent orbit around the Sun. Not a dramatic fall, not a fiery plunge, not the kind of ending we imagine for satellites in low Earth orbit, where atmospheric drag eventually pulls them down. Webb is far too distant for Earth's atmosphere to reach. Its future is more likely to be quiet, orbital, solar and long. This is where the question becomes especially strange. Because if Webb becomes a silent object orbiting the Sun, then it joins the larger collection of solar system bodies, planets, asteroids, dust, old rocket stages, and other bits of human machinery. It will not be special to gravity. Gravity has no museum labels. It does not say, "This one once saw the first galaxies, so handle with care." It treats Webb according to mass, speed, distance, and direction. A golden mirror segment and a small asteroid are both matter-following rules. But to us, of course, Webb is not just matter. It is a memory of our curiosity. That difference exists in our minds, not in the equations. And perhaps that is part of what makes the thought so moving. The universe will carry Webb without knowing what it was, while we, for a little while, know very well. Now stretch that view forward. Not 100 years, not 1,000. Keep going. Civilizations rise and change. Languages vanish and are replaced. Continents continue their slow rearrangement. The moon drifts farther from Earth. The sun grows gradually brighter over time, changing the conditions of the inner solar system. Far in the future, Earth itself becomes less familiar. Oceans do not remain forever. Climate does not remain fixed. The sun, which seems so dependable from one human lifetime to the next, is also aging. In several billion years, it will swell into a red giant, changing the solar system more dramatically than any spacecraft could ever witness while alive. The inner planets may be scorched, swallowed, or transformed. The sun will lose mass, its gravity will weaken, orbits will expand. Later, the sun will shed its outer layers and settle down as a white dwarf, a dense, cooling ember where the familiar daylight star used to be. Where is Webb in all of that? That depends on what has happened to it during the billions of years before. It might still be in some altered solar orbit, farther out after the sun loses mass. It might have been struck by small debris and reduced to fragments. It might have been nudged by a planet, a passing asteroid, or a close stellar encounter. It might be part of a thin population of artificial remnants mixed into natural dust and rock. By 1 trillion years, the solar system will not be the comfortable arrangement we know now. The Sun will be a white dwarf, much dimmer, colder, and older. The planets that remain will move through a changed gravitational landscape. The Milky Way and Andromeda will have merged long before, reshaping the galaxy into a larger stellar system. Many stars will still exist, especially small red dwarfs that burn slowly, but the age of bright young stars will be fading. The sky, if anyone were there to see it, would not be our sky. It is tempting to imagine Webb still whole, a little darkened telescope drifting through that ancient quiet, its mirror perhaps still holding a faint golden shape, its sun shield torn or stiffened or pierced, its instruments cold in a way they were never designed to be. But 1 trillion years is very hard on objects. Tiny impacts matter, radiation matters, temperature cycling matters, the slow accumulation of unlikely events matters. In 1 million years, survival as a recognizable object might be easier to imagine. In 1 billion years, it becomes more doubtful. In 1 trillion years, we're in the realm where almost any small probability has had an enormous number of chances to occur. A dust grain moving fast enough can puncture. A larger micrometeoroid can shatter. Repeated impacts can erode surfaces. A close encounter can change an orbit. Deep time does not need to be violent all at once. It can be violent by patience. Still, we should not rush to erase Webb too quickly. Space is very empty. That is one of the odd comforts of astronomy. Objects can drift for astonishingly long times without touching anything large. The Apollo hardware left on the Moon may last for millions of years. Spacecraft sent beyond the planets may coast between stars for times longer than civilization has existed. Webb's exact fate is uncertain, not because we know it will be destroyed quickly, but because over 1 trillion years the number of possible futures becomes too wide to treat like a simple map. It might become fragments, it might be dust, it might remain partly intact for far longer than seems reasonable, it might orbit the Sun's remnant as a faint artificial asteroid, or it might be altered beyond recognition, no longer Webb in shape, but still Webb in atoms, and there is something worth resting with there. The question, where will James Webb be in 1 trillion years, may not have a single address as an answer. We cannot write down a future coordinate and say here, exactly here, this is where the telescope will be. But we can follow the broad story. It begins near Earth, in a carefully maintained orbit around L2. It continues as a working observatory, seeing ancient light. Then, when the mission ends, Webb becomes a silent object influenced by the Sun, Earth, Moon, planets, sunlight, and time. Over ages, it likely drifts into a solar orbit of its own. Over billions of years, the changing Sun and the changing solar system reshape that path. Over 1 trillion years, Webb may survive only as fragments, dust, or scattered material, unless chance is unusually kind to its structure. In any case, it will no longer be where it began. Nothing will be. That is not a sad answer, or at least it does not have to be. It is simply the scale of things. Every telescope is temporary. Every observatory is temporary. Even stars are temporary, although they take their time about admitting it. Webb's greatness was never that it would last forever. It was that, for a brief and brilliant period, it allowed a small species on a small planet to see farther into darkness than ever before. It took light that had crossed the universe and turned it into images, spectra, measurements, questions, and wonder. It gave us information about worlds we cannot visit, galaxies we cannot touch, and eras we cannot return to. And then, eventually, like all tools, it will become part of the physical universe it once studied. Perhaps that is the softest way to begin this journey. We're not imagining Webb as immortal. We're imagining it as something real. Real things age. Real things drift. Real things are changed by their surroundings. A telescope can begin as a mission and end as an artifact. An artifact can become debris. Debris can become dust. Dust can become part of some future cloud, some future orbit, some future surface, or simply continue moving through the long dark. The atoms do not disappear. They change their arrangements. And in that sense, Webb's far future is not one ending, but many transformations. Far beyond the moon, but still close enough to belong to us in a practical way, the James Webb Space Telescope is quietly circling the Sun. That sounds a little strange at first, because when people imagine a space telescope, they often picture something orbiting Earth, passing over continents, sliding from daylight into night, perhaps looking down now and then like an extremely expensive metal owl. Hubble does something like that. It moves around our planet in low Earth orbit, close enough that astronauts once visited it, repaired it, upgraded it, and gave it a second life. Webb is different. Webb is not looping around Earth like a satellite you could almost imagine chasing with a very determined airplane. Webb is much farther away, about 1.5 million kilometers from Earth, in a region of space that sits beyond the moon in the direction opposite the Sun. That distance is large enough to feel unreal. The moon, our familiar grey companion, is roughly 400,000 kilometers away on average. Webb is around 4 times farther than that. If the moon is the neighbour whose porch light you can still see across the street, Webb is the quiet house far down the road, past the last lamppost where the night seems a little more serious. And yet, in the scale of the solar system, Webb is still close. It is not out near Jupiter. It is not near Saturn's rings. It is not drifting in the deep outer darkness with the comets. It is in Earth's wider neighbourhood, moving around the Sun at roughly the same yearly pace that Earth does. That is the clever trick. Webb is far from us, but not really leaving us. It is like a careful listener walking beside you at a distance, always keeping pace, always just far enough away to hear the universe without the noise of your footsteps. The place Webb occupies is called the Sun-Earth L2 region. It is not a planet, not a rock, not a platform, and not a hidden space station, despite what science fiction might politely suggest after a second cup of tea. It is a gravitational arrangement. The Sun pulls, Earth pulls, Webb moves. And in that combination there are special regions where the motion of a smaller object can stay coordinated with the motion of Earth around the Sun. L2 is one of those regions. It lies on the line from the Sun through Earth and outward, beyond Earth's night side. From Webb's point of view, the Sun, Earth and Moon all remain in roughly the same direction. That single fact is one of the main reasons Webb works so well. It can point its big shield toward the bright, warm things and keep its telescope and instruments facing the cold, dark sky. The sun shield is not just a pretty accessory, it is one of the most important parts of the observatory. Webb observes mostly in infrared light, which means it is looking for heat glow, the faint long wavelength light from distant galaxies, newborn stars hidden in dust, cool planets, brown dwarfs, and the stretched light of the early universe. To see such faint infrared signals, Webb itself must be kept extremely cold. If the telescope were warm, it would glow in infrared light and interfere with its own observations. That would be a bit like trying to listen for a whisper while sitting next to someone vigorously playing the bagpipes. The universe is already quiet enough in infrared. Webb cannot afford to shout over it with its own heat, so Webb hides behind its shield. 5 thin layers spread out like a wide silver kite, each separated from the next so heat can escape sideways into space. On one side, the spacecraft bus, solar panels, communications equipment, and electronics face the Sun, Earth, and Moon. On the other side, the mirrors and instruments sit in the cold. The arrangement is simple in idea and extremely difficult in execution, which is a nice summary of many space missions. Keep the hot side hot enough to function. Keep the cold side cold enough to see. Keep the whole thing pointed properly. Keep communicating with Earth. Do all of this 1.5 million kilometers away, with no mechanic available, no ladder tall enough, and no option to gently tap the side of the telescope if something seems stuck. Right now, when we say Webb is at L2, we do not mean it is sitting exactly on a mathematical point like a pin stuck into a map. It is moving in a halo orbit around that region. A halo orbit is a wide looping path around the L2 area, not around a physical object. This is one of those ideas that sounds as if space has started making riddles on purpose. Webb is orbiting around a place where there is nothing there. But the nothing is not meaningless. It is a point defined by gravity and motion, a useful location created by the relationship between Earth and the Sun. Webb travels around that region in a large looping path while Earth and Webb together continue around the Sun. Imagine walking around a slowly moving carriage while the carriage itself circles a town square. Now make the town square the Sun, the carriage Earth, the walking path L2, and the whole thing invisible. Space does enjoy making simple things more difficult, but it rewards patience. This position gives Webb several advantages. First, it keeps the telescope far enough from Earth that our planet's heat does not constantly wash over it. Earth is warm, the Moon is warm. The Sun is very warm indeed, in case anyone was still undecided on that issue. Webb needs those heat sources kept on one side. Second, because Webb stays roughly aligned with Earth as Earth orbits the Sun, communication is much simpler than it would be if Webb kept disappearing behind the Sun or moving to random parts of the sky. Webb can send its data back to Earth through the Deep Space Network, the system of large radio antennas that talks to distant spacecraft. Every image, every spectrum, every measurement of a galaxy or exoplanet atmosphere has to make the trip home as radio signals. The telescope sees the universe, but Earth still has to listen. There is something quietly charming about that arrangement. Webb is built to study objects billions of light years away, but after it makes those observations, it still has to call home. It is like a traveller standing on a mountain ridge, describing the view to someone back in the village. The view may include ancient galaxies, star nurseries, and worlds around other suns, but the message still returns to a planet with weather, traffic, kitchens, and people checking their phones. A telescope at L2 is not independent in the emotional sense, even if it is physically distant. It depends on commands from Earth. It sends data to Earth. Its schedule is planned by teams on Earth. Its discoveries become papers, images, press releases, arguments, lectures, and late-night moments of wonder on Earth. Webb may be beyond the Moon, but its working life is still tied to the planet that built it. To picture where Webb is tonight, imagine the Sun at the centre of the solar system, Earth moving around it once per year, and Webb riding along outside Earth's orbit, farther from the Sun than Earth by that roughly 1.5 million kilometres. The distance is tiny compared with Earth's distance from the Sun, but it is enough to place Webb beyond our planet's immediate neighbourhood. It is not floating directly in Earth's shadow. In fact, Webb avoids Earth's shadow because it needs steady sunlight on its solar array for power and a stable thermal environment. It does not want to pass in and out of eclipse the way many Earth satellites do. Going from sunlight to shadow and back again causes temperature changes, and temperature changes can make structures expand and contract. For a telescope that depends on the precise alignment of 18 mirror segments, thermal stability is not a luxury. It is part of how the instrument stays sharp. Those 18 mirror segments are another reason Webb feels so unusual. Its primary mirror is not one single solid piece, but a honeycomb of gold-coated beryllium segments, each adjusted with great precision. The gold is not there to look impressive, though it certainly does a good job of that. Gold reflects infrared light very well. The mirror collects that faint ancient light and guides it into instruments that can split it, measure it, and turn it into information. Some of the light Webb receives began its journey before Earth had forests, before fish crawled onto land, before the Sun had even formed, depending on how far away the source is. Webb is located just beyond the Moon, but the light it studies may have crossed almost the entire observable universe. Its address is local. Its attention is cosmic. That contrast is part of the quiet beauty of the mission. Webb sits near Earth in a carefully chosen patch of gravitational usefulness, but it looks outward to places that make the solar system seem like a single speck of dust in a large, quiet room. It studies galaxies from the universe's early history, not because it travels to them, but because their light travels to it. It studies exoplanets, not by visiting them, but by watching how starlight changes when a planet passes in front of its star, or how heat shifts across an alien atmosphere. It studies star-forming regions by using infrared light to peer through dust that blocks visible light. It is not a camera in the ordinary sense. It is a measuring instrument, a cold eye, a patient collector of photons that arrive one by one from places we will never reach by spacecraft. And while Webb is far away by human standards, it is not alone at L2 in the broader history of astronomy. That region has become a favoured home for space observatories because of its stability and its clean view of the sky. Missions such as Gaia have also used the L2 region to make precise measurements. It is a kind of quiet working district for telescopes, though the distances between them are vast, and they are not sitting together like neighbours on a bench. Spacecraft do not wave at each other. They are too busy, too far apart, and frankly not equipped for politeness. But from Earth's perspective, L2 is a useful place to send instruments that need distance, steadiness, and a wide view. Still, Webb does not stay in position by magic. The halo orbit around L2 is not perfectly stable forever. The telescope must make small station-keeping manoeuvres with its thrusters to maintain the desired path. These burns are modest, but important. Without them, small disturbances would gradually move Webb away from its planned orbit. Sunlight itself exerts a tiny pressure. The gravity of the moon and planets adds small tugs. The exact shape of the orbit has to be managed. In that sense, Webb is not parked. It is tended. Its location is an ongoing act of navigation. Ground teams monitor it, calculate corrections, and send instructions. The telescope is quiet in space, but not neglected. It is watched over by mathematics. The fuel used for these maneuvers is one of the practical limits on the mission's lifetime. Webb had a very accurate launch and trajectory, which helped preserve more propellant than might have been used otherwise. That was good news, because every bit of saved fuel can help extend operations. But no spacecraft carries infinite propellant. Over time, station keeping and other attitude control needs use it up. There are other lifetime limits too, of course. Electronics age, detectors degrade, micrometeoroids can strike, mechanical parts can wear or fail. Space is quiet, but quiet does not mean harmless. It is more like an old library where the books occasionally get hit by grains of sand travelling at frightening speed. Even now, Webb bears the reality of being in space. Tiny impacts from micrometeoroids are expected over its lifetime. Engineers designed the observatory with that environment in mind, but no design can make a large mirror completely immune to fast-moving dust. In a human lifetime, such events are manageable risks. In 1 trillion years, they become something else entirely. But we are not there yet. Right now, Webb remains a functioning observatory, not a ruin. It is still in the active part of its story, still gathering light, still helping scientists ask better questions about how galaxies formed, how stars are born, what exoplanet atmospheres contain, and how our own solar system fits into the larger picture. There is a useful gentleness in remembering that Webb is not a spacecraft flying through the universe like a rocket in a movie. It is not heading to Mars. It is not chasing a comet. It is not escaping the solar system. It is, for now, in a special working orbit around the Sun, staying near Earth's line of travel. Its distance from us changes somewhat as it moves around its halo path, but it remains in that broad region beyond the Moon. It is close enough to communicate, close enough to plan observations, close enough that scientists can still think of it as part of Earth's extended scientific reach. but it is far enough that it feels separated from ordinary human life, like an instrument set on a high shelf in a dark room, where it can do delicate work without being disturbed. If you could travel to Webb, which we should say clearly is not something people currently do, the journey would take you far beyond the Moon's orbit. The Moon would no longer dominate the view as it does from Earth's sky. Earth would shrink into a bright disk. The Sun would still be brilliant, dangerous to look at directly, and the sun shield would always have to keep that heat away from the telescope side. You would not find a dramatic landscape there. No cliffs, no dust plains, no craters. L2 is not a place you land. It is a region you occupy by motion. The scenery would be almost entirely darkness, stars, the small bright Earth-Moon system, and the spacecraft itself spread wide and delicate, its shield like a layered sail, its mirror turned away from the glare. That is one reason the phrase "beyond the Moon" is so helpful, but also a little misleading. It gives us a direction, a feeling of distance, a way to place Webb outside the familiar Earth-Moon pair. But Webb is not simply sitting beyond the Moon in a straight line while everything else holds still. Earth is moving around the Sun, the Moon is moving around Earth, Webb is moving around L2, L2 is moving with Earth around the Sun. The whole solar system is orbiting the centre of the Milky Way. The Milky Way itself is moving through the local group. Nothing is fixed. Even a telescope that feels carefully placed is participating in several layers of motion at once. Space is less like a stage and more like a set of moving walkways laid on top of other moving walkways, with everyone pretending this is normal because the equations work. Yet from the viewpoint of mission operations, Webb's position is steady enough to be useful. That is the important part. The telescope can keep its shield oriented. It can maintain communication. It can observe large portions of the sky over the course of its schedule. It can remain cold. The location was chosen not because it is simple, but because it gives the mission what it needs. Astronomy is often a negotiation with inconvenience. Ground-based telescopes must deal with atmosphere, weather, daylight, and city light. Earth-orbiting telescopes must deal with Earth blocking part of the sky, changes between sunlight and darkness, and sometimes the effects of our planet's environment. Webb, placed near L2, avoids many of those problems, though it accepts others. It is too far for easy servicing. It needs precise station keeping. It had to unfold correctly after launch. Every choice in spaceflight is a trade. The fact that Webb unfolded at all still feels remarkable. It left Earth folded tightly inside the nose of its rocket because the telescope was too large to launch fully open. After launch, it had to deploy its solar array, high-gain antenna, sunshield supports, sunshield layers, secondary mirror, radiator systems, and mirror wings. Each step mattered. Each step had to work. By the time Webb reached its working region, it had transformed from a packed machine into a full observatory. So when we imagine it now, beyond the Moon, we are not just imagining an object that was placed there. We are imagining a machine that rebuilt its own observing shape in space, like a carefully packed camping tent that also happens to study the birth of galaxies. This is where its current location begins to connect with its far future. Webb's present life depends on control. Its orbit is maintained, its pointing is managed, its instruments are scheduled, its communications are organized. It is part of a living system of people, antennas, software, power, fuel, and planning. But the physical place it occupies is not permanent in the way a mountain seems permanent. When the active management stops, the balance changes. The region near L2 is useful, but Webb's presence there is an ongoing arrangement, not an eternal promise. That means the story of where Webb will be in 1 trillion years begins with the simple fact that right now, it is being kept where it is. It is a little like watching a candle flame. The flame looks like a thing, stable and shaped, but it is really a process, fed by fuel, oxygen, heat, and flow. Webb L2 is also a process in a sense. It is not just a location. It is a maintained state. Commands go up, data comes down, thrusters occasionally adjust its path. The sun shield holds the thermal balance. The solar array keeps the power flowing, the instruments measure, the mirror gathers. The whole observatory continues because many conditions are being met at once. If those conditions end, Webb does not vanish. But the Webb we know, the active telescope beyond the moon, begins to become something else. For now, though, it remains there, in that quiet region outside the moon's orbit, moving with Earth around the sun. It is close enough that when scientists choose a target, the telescope can be told where to look. It is far enough that its cold instruments can avoid the heat that would blind them. It is distant enough to feel almost unreal, but near enough that every signal it sends can still become a picture on a screen, a graph in a paper, a number in a database, or a moment of amazement for someone scrolling late at night who did not expect to suddenly meet a galaxy from near the beginning of time. So if you step outside tonight and look up, you will not see Webb with your eyes. It is too far and too faint for that, and it is not glowing like a star. But it is up there in the broader sense, not overhead in a simple local way, but somewhere in Earth's extended path around the sun beyond the moon, holding its cold mirror toward the dark. It is one of the quietest outposts of human curiosity, not because it is silent in function, but because its work is done in darkness, patience, and distance. It does not need to announce itself. It simply waits for light that has been travelling for longer than anything human has existed, catches a little of it, measures it carefully, and sends the result back across the gap to the world that made it. One of the easiest ways to misunderstand James Webb is to imagine it as a bigger, newer Hubble, simply parked a little higher above Earth. That sounds reasonable at first. Hubble is a space telescope. Webb is a space telescope. Hubble changed astronomy. Webb is changing astronomy. Both were built to look away from Earth and into the universe. So the mind naturally places them in the same kind of setting, floating above our planet, slipping over oceans and clouds, moving from sunrise to sunset every hour or so, perhaps with Earth rolling beneath them like a giant blue screensaver. But Webb does not live there. Webb is not Hubble with a larger mirror and a fancier sun hat. It is a very different kind of observatory, designed for a different kind of light, and that difference is the reason it had to leave Earth's immediate neighbourhood. Hubble orbits close to Earth, only a few hundred kilometres above the surface. That is high compared with mountains and weather, but not very high by space standards. Hubble circles our planet again and again, completing each orbit in roughly an hour and a half. From that low orbit, it has done extraordinary work. It has looked deep into the universe, measured galaxies, studied nebulae, watched planets, and gave us some of the most famous astronomical images ever made. But Hubble's orbit also came with a very practical advantage. It was close enough for astronauts to visit. That single fact shaped its history. When Hubble launched with a flaw in its mirror, astronauts were able to go up, install corrective optics, and give the telescope the clear vision it was meant to have. Later servicing missions replaced instruments, repaired systems, and extended its life. Hubble was not just a telescope in space, it was a telescope within reach, and that reach mattered. Webb was never designed to live that way. It was too large, too cold, too delicate in its thermal needs, and too dependent on a very specific observing environment. Its main science is done in infrared light. Infrared light is often described as heat radiation, though that can be a little too simple, because not all infrared observations are just about warmth in the everyday sense. But the basic problem is easy to understand. If you build a telescope to see faint infrared signals from distant galaxies, cool stars, dusty star-forming clouds, and planets around other suns, then the telescope itself must not glow too strongly in infrared. A warm telescope is like a person trying to see fireflies while holding a bright lantern in front of their own face. The fireflies may still be there, but good luck noticing them. Webb needed to be kept extremely cold so that it would not blind itself with its own heat. Now imagine trying to keep Webb that cold in low Earth orbit. Every 90 minutes or so it would pass around Earth. It would move between sunlight and darkness. It would see Earth filling a huge part of the sky, glowing with heat in infrared. It would see the moon from changing angles. It would have to deal with repeated temperature shifts as different parts of the spacecraft warmed and cooled. That is not impossible for all telescopes, of course. Hubble works beautifully in its own wavelength range and with its own design, but Webb's sun shield and cold instruments were built for a different arrangement. Webb needed the bright warm things, the sun, Earth, and moon, to stay together on one side, so its shield could block them all at once. Low Earth orbit could not give it that simple geometry. Earth would keep moving around it. The warm planet would not politely stay behind the curtain. This is where L2 enters the story, with a name that sounds much less interesting than it actually is. L2 stands for the second Lagrange point, named after Joseph Louis Lagrange, an 18th century mathematician who studied the way smaller objects can move under the gravity of two larger ones. A Lagrange point is not a place, in the normal sense. There is no island there, no rock, no docking pier, no small sign saying, "Welcome to L2, please enjoy the gravitational balance." It is a location defined by motion and gravity. In the Sun-Earth system, the Sun is the dominant mass, Earth is the smaller but still important companion, and a spacecraft like Webb is tiny by comparison. At certain regions around the Sun and Earth, the gravitational pulls and the spacecraft's orbital motion can combine in a useful way, allowing the spacecraft to keep a stable relationship with Earth as both travel around the Sun. The simplest way to picture it is to imagine Webb moving around the Sun at almost the same yearly pace as Earth. If Webb were simply placed a little farther from the Sun than Earth, without Earth's gravity helping the situation, it would normally orbit the Sun more slowly. Objects farther from the Sun take longer to complete an orbit. Mars takes longer than Earth. Jupiter takes much longer. So a spacecraft outside Earth's orbit would usually fall behind. But near L2, Earth's gravity adds just enough extra pull to help Webb keep pace. It is not that gravity cancels perfectly, and it is not that Webb is weightless in some special way. Webb is always falling around the Sun just as Earth is. The trick is that the combined gravitational influence lets Webb share Earth's orbital rhythm while staying beyond Earth. That is the strange balance. Not balance as in a ball resting at the bottom of a bowl, more like balance as in a cyclist moving steadily, needing motion to remain upright. L2 is useful because of the way things move together. It is part of a rotating system. If you try to imagine it as a still point in empty space, it becomes confusing, but if you imagine the Sun, Earth and Webb all turning together around the Sun, with Webb staying roughly beyond Earth, then the idea becomes gentler. Webb is in a kind of coordinated dance, though a very mathematical one, and thankfully no one has to wear formal shoes. Even so, Webb is not sitting directly on the L2 point. That detail matters. The telescope follows a large halo orbit around L2, so when people say Webb is at L2, they usually mean it is in the region around L2, using that gravitational arrangement. The actual path is wide and looping. It takes Webb months to complete one circuit around that invisible region. This halo orbit keeps the telescope out of Earth's shadow, which is important because Webb needs sunlight for power. Some people imagine Webb hiding in Earth's shadow like a very expensive moth avoiding a lamp, but that is not what happens. If Webb regularly passed through Earth's shadow, its solar array would lose power, and the telescope's temperature would change more dramatically. Webb wants steady sunlight on the warm side and steady cold on the telescope side. It does not want the universe flipping the light switch every few hours. That steady arrangement is the great advantage of L2. From Webb's point of view, the Sun, Earth, and Moon remain in roughly the same direction. Its 5-layer sunshield can face them like a protective wall. On the hot side, sunlight hits the shield and powers the spacecraft. On the cold side, the telescope and instruments can remain at the low temperatures needed for infrared astronomy. It is an elegant solution, though not a simple one. The sunshield is about the size of a tennis court, made from thin layers that had to unfold correctly in space. It is not a solid wall. It is more like several delicate sheets separated by gaps, allowing heat to radiate away between layers. Each layer helps reduce the heat reaching the cold side. By the time you get to the telescope, the difference is enormous. One side is warm enough for spacecraft systems, the other side is cold enough to listen for the faint infrared universe. If Webb had been placed near Earth like Hubble, this shield would have had a much harder job. Earth would sweep around the telescope in the sky, the moon would appear from changing directions, the telescope would move in and out of Earth's shadow, thermal conditions would keep changing, and for Webb, tiny changes can matter. Its mirror segments have to stay precisely aligned. Its instruments have to stay cold and stable. Its observations often require long periods of careful pointing. L2 gives Webb the kind of calm working environment that low Earth orbit could not provide. It is not calm in the sense that nothing moves, everything is moving, but it is calm in the sense that the geometry is predictable and useful. There is another advantage too. At L2, Webb has a broad view of the sky over time. It cannot look everywhere at once, because the sunshield must stay between the telescope and the bright warm objects. Webb has pointing limits. It cannot simply turn around and stare back toward the sun, Earth or moon, because that would expose the cold side to heat and light. But as Earth and Webb move around the sun during the year, different regions of the sky become available. In this way, Webb can observe a large portion of the heavens while maintaining its protective orientation. It is a careful compromise, not complete freedom, but enough freedom to do extraordinary science while staying cold. Communication also works well from L2. Webb is far away but not too far for steady contact. Its signals travel back to Earth across about 1.5 million kilometers, which sounds like a lot until you remember that light crosses that gap in only a few seconds. The data then comes down through radio antennas on Earth. Every observation begins as light from space, becomes an electrical signal inside Webb's instruments, becomes data stored and transmitted by the spacecraft, becomes radio waves crossing the gap, and finally becomes information that scientists can process. It is a long chain, but it is manageable because Webb stays in a predictable relationship with Earth. If it were wandering far around the solar system, communication would be more complicated. If it were too close to Earth, thermal conditions would be worse. L2 is a compromise between distance and connection. This also explains why Webb's location is both powerful and inconvenient. Hubble could be serviced by astronauts because it was close. Webb cannot be serviced in the same ordinary way because it is far beyond the moon. When something goes wrong on Webb, no shuttle crew can simply fly up, open a hatch, and replace a part. There is no short repair visit. Every system had to be designed with care, redundancy, and the acceptance that after launch, the telescope would largely be on its own physically. That may sound risky, and it was. But the reward was an observing environment Hubble could never have had. Space missions often force engineers to choose which difficulty they prefer. Hubble chose closeness and serviceability, while accepting the challenges of low Earth orbit. Webb chose distance and cold stability, while accepting that repairs would be far harder. It is worth pausing over that difference, because it says something about how astronomy has changed. Hubble was built in an era when astronaut servicing was part of the plan. It was a telescope that could grow and recover. Webb was built as an unfolding observatory sent to a remote working place, with its thermal design tied to that place from the beginning. It had to launch folded, then open itself, align itself, cool itself, and begin work. The L2 location was not an afterthought. It was part of the telescope's identity. Its mirror, shield, instruments, orbit, power system, and science goals all fit together. Move Webb into Hubble's orbit, and you do not just change its address, you disturb the logic of the whole machine. L2 may sound like a quiet parking spot, but it still requires maintenance. The halo orbit is not permanently stable without small corrections. Webb must occasionally fire thrusters to stay on its planned path. These maneuvers are called station keeping, which sounds wonderfully ordinary, like sweeping the floor or watering a plant. In reality, it means carefully adjusting the path of a multi-billion-dollar telescope around an invisible gravitational region beyond the Moon. Webb also uses fuel to manage its orientation and unload momentum from its reaction wheels. Reaction wheels help point the telescope without using thrusters constantly, but over time, sunlight pressure and other effects can build up momentum that has to be removed. The details are technical, but the important idea is simple. Webb's current position is actively maintained. It is not nailed to L2, it is guided. This guidance is one reason the question of Webb's far future is so interesting. Right now, its orbit is a controlled state. People on Earth are still part of its motion. They track it, calculate it, adjust it, and keep it useful. But one day, the active guidance will end. When that happens, Webb will no longer remain neatly in the orbit chosen for science. It will begin to drift away from the managed halo path. Not instantly, not dramatically, like a spaceship suddenly thrown into the void. More like a boat whose engine has gone quiet in a slow current. At first, it may seem almost unchanged. Then the differences grow. The same L2 region that once helped Webb work will no longer hold it in exactly the way mission planners intended. This is because L2 is not the kind of stable place where objects naturally settle forever. Some Lagrange points are more stable than others. In the Sun-Earth system, L4 and L5, which lie ahead of and behind Earth in its orbit, can be more naturally stable for small objects under the right conditions. L1, L2 and L3 are more delicate. A spacecraft can operate there, but it needs correction. The word balance can mislead us if we picture a marble sitting at the bottom of a bowl. L2 is more like a marble near the top of a rounded hill, except the hill is made of gravity, motion and rotating coordinates, which is not the most convenient playground equipment. With careful nudges, the marble can stay near the top. Without nudges, it slowly wanders away. For Webb's mission, that is perfectly acceptable. Spacecraft are designed for missions, not eternity. They carry enough fuel and redundancy to work for many years, not for the age of stars. The L2 environment gives Webb what it needs during its active life. It does not need to be permanent. But when we look ahead to 1 trillion years, the temporary nature of that arrangement becomes the beginning of a much longer story. Webb's future will not be a simple case of still at L2. It will not remain forever in the working position that made its science possible. Eventually, without station keeping, it will leave the carefully maintained halo orbit and enter some other path around the Sun. That path will depend on the exact circumstances when control ends. Small differences in speed and direction can matter over long times. The timing of the final maneuvers, the amount of fuel left, the pressure of sunlight on the sun shield, the gravitational nudges from the Moon and planets, all of these can influence the drift. This is why predicting the exact position of Webb in the far future is not like calculating where a train will be on a track. It is more like predicting the future of a leaf released into a huge, slow river, except the river is gravity, the leaf is a telescope, and the banks are moving too. You can describe the broad behaviour, but the exact details become uncertain as time stretches. Still, the broad picture is clear enough to follow. Webb is near L2 because that region lets it stay cold, maintain a stable relationship with Earth, communicate effectively, and observe the infrared universe without the Sun, Earth, and Moon wandering all around its sky. It does not orbit Earth like Hubble because an Earth orbit would bring heat, shadow, changing thermal conditions, Earth blockage, and a geometry that does not suit Webb's shield. Hubble's orbit was right for Hubble. Webb's orbit is right for Webb. They are not rivals in this sense. They are two different answers to two different engineering questions. Hubble needed access, repairability, and a powerful view from above the atmosphere. Webb needed cold, distance, and a stable, shielded environment. One stayed close enough for astronauts to touch. The other went far enough to become cold and quiet. The difference can feel almost personal. Hubble is like an observatory on a high mountain that people can still climb to repair. Webb is like an observatory, placed on a remote ridge beyond the last road, where it can see better, because almost nothing nearby disturbs it. Hubble looks at the universe while repeatedly circling the world that made it. Webb looks outward from a place where Earth is kept behind the shield, present but not intrusive. Hubble's home is close, dynamic and familiar. Webb's home is distant, controlled and strange. Both are extraordinary. But only Webb's location makes tonight's question feel so large, because Webb has already taken the first step away from ordinary Earth-centered time. And there is another quiet detail here. Webb is not beyond Earth, because it is trying to escape us. It is beyond the moon, because it must be. Its distance is a tool. The cold is a tool. The orbit is a tool. L2 is not a destination chosen for drama, but for function. That is often how the most beautiful space missions work. They do not begin with romance. They begin with requirements. The telescope must be cold. The shield must face the heat. The mirror must stay aligned. The spacecraft must have power. It must talk to Earth. It must see enough of the sky. From those practical needs, a strange and beautiful arrangement emerges. A golden mirrored observatory circling an invisible gravitational point, far beyond the moon, watching ancient light. So when we ask why James Webb does not orbit Earth like Hubble, the answer is not simply that farther is better. Farther is not always better. A telescope near Earth can be serviced. It can transmit data easily. It can be reached, at least in principle. But Webb needed a particular kind of far. Far enough from Earth's heat. Far enough for the sun, Earth and moon to stay on one side. But not so far that communication and power became unreasonable. L2 provides that balance. It is the right kind of distance. A place that is not really a place. A point that is not really occupied. An orbit around a mathematical neighbourhood that keeps a telescope cold enough to see the faint glow of the early universe. The working life of James Webb is not measured by one single clock. It is measured by fuel, by temperature, by electronics, by tiny moving parts, by detectors, by mirrors, by software, by radiation, by micrometeoroids, and by the quiet daily discipline of keeping a complex machine healthy far beyond the moon. When we ask how long Webb can keep working before it falls silent, we're not asking when the telescope simply runs out of interest in the universe, as though one day it looks at another galaxy and thinks, you know what, I have seen enough. We're asking how long a real spacecraft, built with real materials and real limits, can continue doing very delicate work in an environment that is beautiful, useful, and not especially forgiving. Webb was originally planned with a minimum mission of at least 5 years and a goal of 10 years. That was the cautious promise, the practical target around which the mission was designed. 5 years would already have been enough to change astronomy. 10 years would have been a triumph. But Webb's launch was so accurate and its early course corrections were so efficient that much less propellant was used than expected to get it onto the right path. That mattered enormously. Space telescopes at L2 do not need fuel in the way a car needs petrol to keep rolling down a road. Webb is not constantly firing engines to move forward. It is already moving under gravity, but it does need propellant for small, careful adjustments to maintain its halo orbit around L2 and to manage its orientation in space. So the fuel is less like the energy for a long road trip and more like the gentle nudges needed to keep a balancing act balanced. Because of that saved propellant, Webb is expected to have enough fuel to support science operations for more than 20 years, assuming other systems keep working. That little phrase, assuming other systems keep working, is doing a lot of quiet labour. It is the sort of phrase engineers understand very well, because no machine is only one thing. A telescope is not simply a mirror. It is a whole body of systems, each depending on the others. The mirror can be perfect, but if pointing fails, the science suffers. The instruments can be ready, but if communication fails, the data cannot come home. The spacecraft can have fuel, but if electronics degrade, commands may not be carried out. The sunshield can keep everything cold, but if thermal control changes too much, observations may become harder. Webb's life is not a single candle burning down at a steady rate. It is more like a quiet house with many rooms, and the mission continues as long as enough lights remain on in the right places. Fuel is still one of the clearest limits, because it is finite and cannot currently be refilled as part of normal mission operations. Webb uses propellant for station keeping, those small thruster burns that keep it near its intended halo orbit around L2. Without those burns, Webb would gradually drift away from the carefully maintained path that makes its science possible. The telescope also uses propellant for momentum management. This sounds like something you might need after eating too much pudding, but in spacecraft terms it is serious. Webb uses reaction wheels to help point itself. These wheels spin inside the spacecraft, changing speed to rotate the observatory without wasting fuel every time it needs to turn. But sunlight pressure and other small effects slowly add momentum to the system. Eventually, that stored momentum has to be unloaded with thrusters, so even pointing a telescope in space, which sounds so clean and graceful from a distance, involves a slow, practical bookkeeping of forces. This is one of the reasons the mission lifetime cannot be infinite. As long as Webb is doing science, it has to point accurately, stay thermally stable, communicate, and remain near the correct orbit. Each of these needs support. Each support system has a limit. Even a calm telescope must keep correcting itself. Space does not provide a perfectly still table on which to set your instrument. It provides motion, radiation, sunlight pressure, gravity from several bodies, and tiny disturbances that grow if they are ignored. Webb's silence will not come because the universe becomes boring. It will come when the observatory can no longer maintain the conditions needed to keep listening properly. But fuel is not the only concern. The harsh environment of space slowly works on hardware. Radiation can affect electronics and detectors. Charged particles from the sun and cosmic rays from beyond the solar system pass through space all the time. Spacecraft are built with shielding, redundancy, and fault protection. But over many years, radiation can still cause damage. Sometimes it produces temporary glitches. Sometimes it gradually degrades sensitive components. The longer a mission operates, the more it relies not only on its original design, but on the careful work of engineers who monitor behaviour, update procedures, adjust settings, and learn the personality of the spacecraft. Every long-lived mission becomes, in a sense, a relationship. The teams on Earth learn what the observatory likes, what it tolerates, what needs watching, and which little signs mean, please pay attention to this before it becomes a problem. Webb's instruments are another part of the story. They are not all identical, and they do not all operate in exactly the same way. Webb carries instruments designed to image and analyze light across near-infrared and mid-infrared wavelengths. Some parts are passively cooled by the sunshield and the coldness of space, while the mid-infrared instrument needs an active cryocooler to reach especially low temperatures. That cryocooler is one of the quiet heroes of the mission. It keeps part of the observatory cold enough to see wavelengths that would otherwise be overwhelmed by heat. As long as it works, Webb can explore a deeper range of infrared light. If it ever failed, the whole telescope would not necessarily become useless, but some observations would be lost. That is often how space missions age. They do not always stop all at once. Sometimes they lose one ability, then another, while still finding ways to do valuable science with what remains. This is worth remembering because full silence sounds like a single dramatic moment. A switch flips. A signal stops. Earth waits. Nothing answers. That can happen, of course, and it has happened to spacecraft before. But often a mission declines more gradually. An instrument weakens, a mode becomes unavailable, a wheel fails and the team develops a workaround. A detector becomes noisier, a heater, sensor, transmitter or control system begins to misbehave. Engineers adapt. Scientists adjust observing plans. The observatory does less than it once did, but still does enough to matter. Hubble itself has shown this kind of resilience again and again. Chandra has too. Space missions can become old and still useful, like a trusted old radio with a crackling speaker that still catches a distant station on a clear night. Webb was designed with redundancy, meaning some systems have backups or alternate ways to operate. Redundancy is one of the quiet arts of spacecraft design. You cannot send a repair person easily, so you build in second chances. Not infinite chances, because mass, complexity and cost all matter, but enough to survive likely problems. A spacecraft is full of careful compromises. Add more backup systems and you add mass. Add more mass and launch becomes harder. Add more complexity and there are more things that can fail. Remove too much and the mission becomes fragile. Somewhere between those extremes, engineers make thousands of decisions, each one trying to give the telescope the best chance of a long life. Then there are micrometeoroids. Space looks empty from far away, but it contains dust grains and tiny particles moving at high speeds. Over a few years, Webb expects some impacts. Its mirror and shield were designed with this environment in mind. A small impact does not automatically end the mission. The mirror is segmented, the observatory can be adjusted, and engineers can account for some damage. But the risk never becomes zero. A grain of dust in space is not like a grain of dust on a table. When it is moving fast enough, it can behave like a tiny bullet. Over decades, the number of small impacts increases. Most will be minor, a few may be more noticeable. The question is not whether Webb will remain perfectly untouched. It already lives in the real universe, not in a museum display case. The question is how well it can continue performing despite the small scars that space leaves behind. The sun shield also matters. It is large, thin, and essential. It keeps Webb cold by blocking heat and light from the sun, Earth and Moon. It is made of multiple layers, each helping to reduce the heat that reaches the telescope. The shield does not have to remain cosmetically perfect to work, and it was designed with some tolerance for small damage. But its health is important. If the shield were badly damaged, temperatures could change, and infrared observations could suffer. A telescope like Webb depends on thermal stability. Metal and other materials expand and contract with temperature. Instruments behave differently when warmed. Detectors become noisier. The whole observatory is designed around the idea that one side is warm and powered, while the other side stays cold and shielded. Disturb that balance enough, and the telescope is still physically there, but the quality of its science changes. Communication is another possible path towards silence. Webb sends data to Earth by radio. As long as the transmitter, antenna pointing, onboard computers, power systems and ground network all cooperate, the light collected by Webb can become data on Earth. If communication failed completely, Webb might still physically collect light for a while, but the observations would no longer reach us. That is a strange thought. A telescope could, in theory, keep pointing at the universe but become unable to tell anyone what it sees. In practice, spacecraft are designed to enter safe modes and await commands when something goes wrong. They are not independent explorers making poetic decisions in the dark. They are machines following instructions and protective logic. Still, communication is the thread connecting Webb's cold mirror to human understanding. Without that thread, the mission as we experience it would end. Power matters as well. Webb uses a solar array to generate electricity. Unlike some outer solar system spacecraft that rely on nuclear power because sunlight is weak far from the sun, Webb is close enough to the Sun for solar power to work well. Its orbit near L2 was chosen partly to avoid eclipses, so the solar array can keep producing power steadily. But solar arrays also age. Radiation and micrometeoroid damage can reduce their performance over time. Electronics need power, heaters need power, instruments need power, communication needs power. If available power falls too low, operations have to be reduced. Again, the decline might be gradual. The telescope might do less, conserve more, choose priorities carefully. Long missions often become masters of adaptation. The attitude control system is another quiet necessity. Webb must know where it is pointed, and it must point with extreme precision. It uses star trackers, gyroscopes, reaction wheels, fine guidance systems, and a fine steering mirror to keep targets stable in its instruments. For us, looking at a star is as simple as tilting our head. For Webb, holding still on a target while orbiting near L2, while sunlight presses on the sunshield, while internal wheels spin, while tiny vibrations exist, is an engineering achievement. If pointing accuracy degraded too much, Webb would not necessarily be dead, but many observations would become difficult or impossible. The universe is faint. A little blur, a little drift, a little instability can turn precious data into something much less useful. And then there is the simple issue of time. Time itself is not a failure mode, but time allows all failure modes to gather. Every spacecraft begins with margins. Fuel margin, thermal margin, power margin, pointing margin, data margin, structural margin. Over years, those margins can shrink. A part that was new becomes old. A surface that was clean becomes weathered by radiation. A detector that was sharp becomes noisier. A system that had several backup paths loses one. Teams compensate, but compensation is also finite. The great hope for Webb is not that it remains young forever. The hope is that it ages slowly, usefully and gracefully, giving astronomers as many years as possible before its limits become too large. It is also important to understand that Webb's science lifetime and Webb's physical lifetime are not the same thing. The science lifetime is how long it can operate as a useful observatory, collecting data and returning it to Earth. The physical lifetime is how long the object itself remains in space. Webb will not disappear when the mission ends. It will not dissolve because the last command has been sent. It will still be a spacecraft, still made of mirror segments, shield layers, support structures, tanks, cables, instruments and electronics. But at some point it may no longer be able to do the job it was built for. That moment is when the observatory becomes an artifact. There is something very human about that distinction. A musical instrument can remain beautiful after it can no longer hold tune. A lighthouse can still stand after its lamp goes dark. A book can survive long after its language is no longer spoken. In the same way, Webb may remain physically present after its working voice has faded. Its silence will not mean it has become meaningless. It will mean its active partnership with Earth has ended. For years or decades, it gathers light and speaks in data. Afterward, it becomes a silent record of a civilization that wanted to see where it came from. When might that happen? The honest answer is that no one can give an exact date. More than 20 years of potential science lifetime is an estimate based largely on propellant and mission performance. But spacecraft sometimes surprise us in both directions. Some last far longer than expected. Others encounter failures no one can fully predict. Webb could keep working into the 2040s if its systems remain healthy. It might lose some capability before then. It might continue beyond the main expectation in reduced form. The future of a complex spacecraft is not a neat appointment in a calendar. It is a set of probabilities watched carefully by people who know that every extra year of data is a gift. For astronomers, the question of Webb's remaining lifetime shapes how observations are planned. Time on the telescope is precious. Scientists submit proposals, panels review them, and the most valuable observations are scheduled. If Webb may work for many decades, There is room for long programs, repeated monitoring, ambitious surveys, and follow-up discoveries that no one has imagined yet. If some system begins to degrade, priorities may shift. This is another way a telescope's life is measured, not just in years, but in choices. What should Webb look at while it can? Which questions are urgent? Which targets will still be there later, and which events are temporary? Supernovae fade, comets pass, planetary weather changes, galaxies wait patiently, but some cosmic moments do not. Webb's silence, whenever it comes, will likely arrive after an enormous amount of work. By then, it will have observed the early universe, studied stars being born, examined planets in our own solar system, explored atmospheres of worlds around other stars, and measured objects too faint or too cool for many previous instruments. It may have helped identify molecules in distant atmospheres. It may have refined our understanding of galaxy formation. It may have complicated our theories, which is one of science's favourite ways of being helpful. A telescope does not need to answer everything to succeed. Sometimes the best mission is one that reveals our questions were smaller than reality. And after Webb falls silent, Earth will still remember it for a while. Its data archive will remain. Scientists will continue studying observations already collected. New methods will pull new meaning from old data. Students not yet born when Webb launched may publish work based on light it gathered years earlier. This is another kind of afterlife for a telescope. The machine stops observing, but its data keeps speaking. Hubble's archives have done this. Other observatories have done this. Webb's archive may remain scientifically valuable long after the last signal from the spacecraft. The telescope's working life in space is limited, but its scientific life on Earth can stretch beyond the moment of silence. Eventually, though, even memory changes. Archives are copied, translated, stored, lost, recovered, or forgotten depending on what happens to civilization. In our near future, Webb's data will be treasured. In deep future terms, even the record of Webb may become uncertain. But that belongs to the longer journey ahead. For now, it is enough to understand that Webb's active lifetime is expected to be measured in decades, not centuries, not millennia, and certainly not 1 trillion years. Its instruments are made for a mission, not eternity. Its fuel supports careful operation, not endless station keeping. Its parts are durable, but not immortal. The observatory is extraordinary, but it is still a machine. That makes its work more precious, not less. The fact that Webb will fall silent gives weight to each observation. Somewhere beyond the moon, near a balance point that is not truly a place, a cold telescope is spending its finite years collecting ancient light. It has a limited supply of fuel, a limited reserve of hardware health, a limited number of years in which Earth can ask it to look, and within that limit it sees things that would otherwise remain hidden. It turns its temporary life into a record of galaxies, stars, planets, dust, chemistry, and time. Webb will not work for 1 trillion years. It will not keep adjusting its orbit through the age of stars. It will not remain an active telescope when the sun grows old, when Earth changes beyond recognition, or when the galaxy itself has taken on a different shape. Its science lifetime is likely decades if all continues well. Perhaps more than 20 years from its carefully saved propellant, but limited by the realities of space hardware. Then one day, whether gradually or suddenly, the stream of new observations will end. The cold mirror may still exist, the shield may still catch sunlight, the structure may still move through space, but the conversation between Webb and Earth will have gone quiet, and the observatory will begin the next part of its existence, no longer a working telescope, but a silent object left to gravity, sunlight, and time. When a space telescope finishes its mission, it does not simply end in the way a story ends when you close a book. There is no neat final page in space, no soft click of a cover, no librarian coming by to put the telescope back on a shelf. A space telescope is a physical object, and physical objects continue. They keep moving, they keep warming and cooling, they keep being pulled by gravity, pushed by sunlight, struck by tiny particles, and slowly changed by the environment around them. The science may stop, the signal may fade, the people on Earth may eventually stop sending commands, but the telescope itself remains somewhere, doing the one thing matter is very good at doing: existing. For a telescope close to Earth, the end can be fairly dramatic, at least compared with the quiet life of Webb. Many satellites in low Earth orbit are slowly pulled down by the thin upper atmosphere. That atmosphere is extremely faint, almost nothing by the standards of air you could breathe, but it is not completely absent. At those altitudes, even a tiny amount of drag can matter over time. Each orbit loses a little energy, the path lowers, the spacecraft dips deeper into thicker air. Eventually the descent accelerates, then comes re-entry, heat, plasma, breakup, and in most cases burning high above the surface. For a low-orbit spacecraft, Earth is always reaching up with a very thin, invisible hand. It may take years or decades, but the hand is there. That is not Webb's situation. Webb is far beyond the reach of Earth's atmosphere. It is not skimming around the planet every 90 minutes like Hubble. It is not gradually losing height because of atmospheric drag. It is not waiting for the upper air to tug it down. Webb is out near the Sun-Earth L2 region, moving around the Sun while maintaining a relationship with Earth. So after its mission ends, it will not fall back to Earth in a fiery farewell. There will be no bright streak across the sky for someone to point at and say, "There goes Webb." It will not come home like that. Its end will be quieter, colder, and much longer. This difference matters because spacecraft retirement is not one universal process. What happens to a mission after its active life depends on the orbit, the fuel left, the risks to other spacecraft, the design of the vehicle, and what can still be controlled at the end. Some spacecraft are deliberately guided into Earth's atmosphere so they burn up safely. Some are moved into graveyard orbits, places where they are less likely to interfere with active satellites. Some are left in stable paths when no practical disposal is possible. Some are passivated, which means stored energy is reduced as much as possible. Batteries may be discharged, fuel lines depressurized, and systems made less likely to explode later. It is one of the less glamorous parts of spaceflight, but it is important. Even after a spacecraft stops working, it can still become a hazard if it breaks apart or wanders into a crowded region. For Webb, the crowded region is not the same as low Earth orbit or geostationary orbit. There are other spacecraft near L2, and future missions may also use the region, but it's not crowded in the familiar satellite traffic sense. Distances are large, orbits are carefully tracked. Webb is in a halo orbit around a gravitational region, not in a tight shell around Earth. The practical end-of-mission concern is less about immediate collision with a swarm of nearby satellites, and more about what trajectory Webb will follow once it no longer has fuel or operational control to remain where it was. As long as Webb is alive, mission teams can keep it in the right region. After the active mission, if there is enough capability left, operators may choose a disposal maneuver that moves it away from the operational L2 neighborhood and onto a safer long-term solar orbit. That is the kind of quiet goodbye a telescope like Webb is more likely to receive. Not a crash, but a careful push. A careful push sounds simple, but the timing and planning matter. Spacecraft near L2 are not parked in ordinary parking spaces. They are moving around a region shaped by gravity and orbital motion. Webb's halo orbit is maintained by periodic station-keeping maneuvers. If those maneuvers stop, Webb will slowly leave the controlled path. If operators still have enough propellant and control near the end, they can use that remaining ability to influence where it goes next. A disposal maneuver could send it into an orbit around the Sun that no longer repeatedly returns it to the same operational zone near L2. The goal would be to reduce the chance that a dead Webb becomes a problem for future missions that may also want to use that region. In other words, even at the end, Webb may receive one last act of navigation. This is one of the strange dignities of spacecraft. Their final commands are often not about discovery, but responsibility. During the active mission, commands tell Webb where to point, what to observe, when to transmit data, how to manage its systems. Near the end, commands may become simpler and heavier. Move here, burn this much, turn this way, make yourself safe. Empty or secure what can cause trouble later. Reduce pressure, reduce stored energy. Stop being a spacecraft that needs care and become an object that will not make the environment worse. It is not romantic in the usual sense, but it is a form of care. Space is not a place where we can easily clean up after ourselves, so the best cleanup is often to think ahead. If Webb still has working systems when the decision comes, the end might be orderly. The science program would wind down. Engineers would assess the spacecraft's health. Remaining fuel would be calculated carefully, because in space you do not want to spend your final fuel discovering that you needed a little more final fuel. Commands would be tested, checked, and sent. Webb might perform a last maneuver, leaving its carefully maintained halo orbit and entering a solar orbit of its own. Communications might continue for a while after that. The telescope could still report its status, perhaps sending engineering data rather than cosmic images. Then, eventually as power, pointing, fuel, or communication failed, the signal would stop. Not because Webb has gone anywhere dramatic, but because the living connection has ended. There is another possible version, less tidy but still realistic. Webb could suffer a major failure before a planned disposal. A critical system might stop responding. A communication issue might prevent further commands. A safe mode might not recover. A fuel problem might leave too little control. In that case, Webb might drift away from its maintained orbit without a final carefully chosen maneuver. This would not necessarily be catastrophic. Space near L2 is vast, and the natural drift would eventually move it away from the precise working orbit. But the difference between a planned retirement and an unplanned silence is important to engineers, because planned endings give more control over long-term risk. Space missions, like people, prefer to leave things in good order when they can. Once Webb is no longer a working telescope, its identity changes. During its mission, Webb is an observatory. It is scheduled, commanded, calibrated, and listened to. After the mission, it becomes a spacecraft remnant. Later still, it becomes debris in the broad physical sense, though not necessarily dangerous debris. That word can sound harsh for something so important, but space does not categorize objects by meaning. A dead telescope, an old upper stage, a lost bolt, a natural dust grain, and a chip from an ancient collision are all pieces of matter in motion. Humans may know which one once measured the atmosphere of a distant planet. Gravity does not. And yet, even as a silent remnant, Webb would not immediately look like nothing. For some time, perhaps a very long time, it could remain a recognizable object. Its golden mirror segments would still be arranged, unless damaged. Its sunshield layers might still be spread, though aging, punctured, and slowly changed by the harshness of space. The spacecraft bus would still hold its components. The solar array might still catch sunlight, even if no useful power flowed where it was needed. If another spacecraft could fly beside it after the mission ended, which is not part of Webb's current story but is interesting to imagine, it might see a quiet observatory no longer doing science, like an abandoned observatory dome on a mountain after the astronomers have left. The structure remains, but the night is no longer being measured from inside. What happens next depends on time. In the first years after the mission, Webb would still be Webb in the visual sense. It might be tumbling slowly or maintaining some passive orientation depending on how its systems failed. It might still be in a solar orbit near Earth's general path, or moving away from the L2 region into a disposal orbit. It would be silent, but not ancient. If anyone still tracked it, they could calculate its path, perhaps observe it as a faint moving dot with powerful telescopes. It might be catalogued, discussed, remembered, and perhaps visited by a future robotic mission if a future civilization decided that old observatories deserved archaeology. That may sound fanciful, but people already care deeply about artifacts from early spaceflight. We preserve old capsules, track the voyagers, and know where Apollo hardware rests on the moon. It is not impossible that future people might treat Webb as a relic worth finding if they can. Over decades and centuries, the situation changes. Webb would be exposed to sunlight, cosmic rays, charged particles, and micrometeoroids. The materials would age. Some surfaces would darken or become brittle. Thin layers might tear from small impacts or from stresses caused by temperature changes. The mirror segments, made from beryllium and coated with gold, might endure physically for a long time, but their precise alignment would no longer matter. A telescope's mirror is only a scientific instrument when it is held, pointed, cooled, and focused as part of a working system. A misaligned mirror segment in deep space is still beautiful perhaps, but it is no longer measuring the beginning of galaxies. The sun shield would be especially vulnerable because it is broad and thin. Its size, which made it useful for blocking sunlight, also makes it a large target over long periods. A tiny particle crossing space at high speed can make a hole. Many tiny particles can make many holes. A larger impact could tear or fragment part of it. This does not mean the shield would quickly vanish. Space is sparse, but over long enough periods, delicate structures have many opportunities to be damaged. A tennis court-sized shield is excellent for cooling a telescope during an active mission. It is not a promise of trillion-year preservation. The main body of Webb might last much longer than the shield as a collection of connected parts, but deep time is patient. Micrometeoroid impacts can chip, puncture, and slowly fragment. Radiation can alter materials. Thermal cycles can stress joints. If Webb is in a solar orbit, its distance from the Sun and its orientation will affect how much heating and cooling it experiences. If it tumbles, different surfaces may face sunlight at different times. If it remains in a more stable attitude for a while, some sides may age differently from others. The details would be complicated, and after the mission ends, no one may be receiving the data needed to know exactly what is happening. There is a quiet irony here. Webb was built to reveal the past by catching ancient light, but after it falls silent, its own future becomes increasingly hidden from us. Unless we track it, visit it, or maintain records of its orbit, Webb could gradually become a lost object. Not lost in the sense that it has vanished, but lost in the human sense. Its path might become uncertain, its condition unknown, its name preserved in archives while the object itself drifts somewhere no one has checked in a long time. Space is full of things that exist without being watched. Most of the universe is like that. Webb would simply join the majority. If a future disposal places Webb into a heliocentric orbit, an orbit around the Sun, then it becomes one of countless objects circling our star. Natural asteroids do this. Comets do this. Dust grains do this. Human-made spacecraft and rocket stages do this too. Some follow paths that cross near Earth's orbit. Some stay inside or outside. Some are disturbed over time by planets. Jupiter, especially, is very good at rearranging smaller bodies. Its gravity can shift orbits, scatter objects, and change long-term outcomes. Over thousands, millions, or billions of years, even small gravitational tugs can matter. Webb's orbit after mission end would not be frozen in perfect repetition forever. It would evolve. Could Webb ever hit Earth after its mission? From its current L2 environment, that is not the natural simple ending. It is far beyond low Earth orbit and not being dragged down by atmosphere. A planned disposal would likely aim to avoid future interference with Earth and operational regions. In orbital dynamics, though, very long times can create surprising possibilities. Objects in solar orbit can have close encounters, and close encounters can change paths. But for the near and medium future, Webb's story is not a return to Earth. It is a departure from its maintained working orbit into a quieter, less controlled path around the Sun. Could Webb hit the Moon? Could it hit another planet? Again, over short human timescales, such outcomes are not the expected script. Space is large. Planets are small targets in that largeness. Orbital paths can be predicted for a while, but uncertainty grows over long periods. Over deep time, possibilities widen, but the most likely broad idea is not an immediate collision. It is drifting, orbiting, being perturbed, aging, and perhaps slowly fragmenting. Space often destroys not through one grand event, but through a long series of small ones. There is also the question of whether Webb could be rescued or refueled someday. Webb was not designed for routine servicing the way Hubble was, but future space technology may become far more capable than ours. Robotic servicing near L2 is not impossible in principle. A future mission could inspect Webb, nudge it, repair something or move it, if there were enough reason and capability. This is speculative, of course. We should not build our answer on rescue as if it is guaranteed. But it is worth acknowledging that Webb's end is not purely determined by physics alone. Human choices, or the choices of whatever civilization follows us, could alter it. A telescope can be abandoned, preserved, moved, or visited. The future is not only gravity, it is also intention, at least for as long as intention remains in the neighbourhood. But let us imagine the simplest path. Webb works for decades, its systems age, its mission ends. If possible, it is commanded into a disposal orbit around the Sun, away from the operational L2 region. It is passivated as much as practical. Its transmissions cease, then it drifts. For a while, it remains a recognizable spacecraft. Later, it becomes damaged, altered, perhaps partially fragmented. Its orbit changes slowly under the influence of the Sun, planets, and radiation pressure. Its materials continue through space. Some pieces may remain together for very long times, others may separate. The telescope becomes less an object and more a cloud of possible futures. This is not failure. It is what happens to machines after their purpose is complete. A mission is not meant to last forever. It is meant to do something valuable while it can. We do not judge a candle by whether it burns for 1 billion years. We judge it by whether it gave light when light was needed. Webb's purpose is to collect faint infrared light and help us understand the universe. When that purpose ends, the object remains, but the mission has already given what it could. Its afterlife is physical rather than scientific, unless future beings choose to make it scientific again by studying the relic itself. That thought opens a gentle possibility. Long after Webb's final observation, the telescope could become an archaeological object, not for us perhaps, but for descendants or future explorers. A silent golden mirror in solar orbit would say something about the people who made it. It would say that we reached beyond our atmosphere, placed a cold telescope near a gravitational balance point, and used it to study galaxies, stars, planets, and the origins of cosmic structure. It would say that before we knew how long we would last, we cared enough to look. Even if no one finds it, that was still true, and if no one ever visits it, Webb's atoms continue anyway. Some may remain in mirror segments, some may flake away in tiny fragments, some may be knocked loose by impacts, some may eventually be swept into other bodies or scattered into new orbits. Matter is patient with identity. It does not mind being called telescope, debris, dust, or relic. Those names are ours. The atoms simply follow the rules. So after its mission ends, Webb does not end all at once. It leaves the realm of active astronomy and enters the realm of orbital afterlife. Its first future may be planned by engineers. Its later future will be shaped by gravity, sunlight collisions, and deep time. It will no longer send us the early universe. It will no longer adjust its mirror for a distant galaxy or hold steady on a planet crossing its star. But it will remain part of the solar system's inventory, a human-made object moving among natural ones, slowly becoming less like a telescope and more like a trace. After the last planned command, after the last observation has been stored, after the last useful signal has crossed the distance back to Earth, James Webb would not stop moving. That is the first thing to keep in mind. A space telescope can fall silent, but it cannot step out of the solar system's motion like someone leaving a quiet room. Even when it no longer listens to Earth, even when Earth no longer listens back, Webb still has speed. It still has mass. It still belongs to the sun's gravity. And so its next life, if we can call it that, would likely be a long drift around the sun, no longer guided as a working observatory, but still carried along by the same star that once powered its instruments. This can be a little hard to picture, because the word drifting can make something sound lazy or random, like a leaf wandering across a pond. But in space, drifting usually means following an orbit. It does not mean Webb simply floats away in a straight line, lost into whatever direction it happened to face when the mission ended. The telescope would already be moving around the sun, because everything near Earth is moving around the sun. Earth does it once per year. The Moon does it along with Earth. Webb does it too from its region near L2. When active station keeping stops, Webb's carefully maintained path around L2 would gradually change, but it would not suddenly forget the sun. It would become a heliocentric object, an object orbiting the sun, unless some future maneuver or later gravitational encounter sends it somewhere else. A heliocentric orbit is a simple phrase for a very large idea. It means the sun becomes the main object determining Webb's path. Webb would join the same broad family as asteroids, comets, planets, old rocket stages, dust grains, and the small human-made objects that have been left in independent paths around the sun. Some of those objects are natural and ancient. Some are recent and artificial. Gravity does not separate them into categories. It simply pulls. Webb's golden mirror, its sun shield, its fuel tanks, its instruments, and its silent electronics would all continue moving according to the same rules that move a stone, a comet nucleus, or a lost screw from a rocket stage. The difference would be meaning, and meaning is something we bring with us. To the sun, Webb is only a small object in orbit. To us, it is a machine that once looked almost back to the beginning of time. For the first years after the mission, if Webb has been placed into a disposal orbit, it might remain fairly close to Earth's general orbital neighbourhood, although no longer near the useful L2 path in the way it was during science operations. Its orbit would depend on the final manoeuvre, the timing, the remaining fuel, and the exact state of the spacecraft. If no disposal manoeuvre were possible, it would leave the maintained halo orbit more naturally, slowly wandering away from the controlled region because L2 does not hold objects perfectly without correction. In either case, the change would not look dramatic from far away. There would be no explosion, no sudden fall, no theatrical goodbye. Just a slow, growing difference between where Webb used to be kept and where gravity now allows it to go. For a while, Webb would still look like Webb. Its sunshield might remain spread. Its primary mirror might remain in its 18-segment shape. The secondary mirror would still sit out in front on its supports. The spacecraft bus would still be attached behind the shield. It might turn slowly if its attitude control system no longer holds it steady. It might keep some orientation for a time, depending on how the final systems fail. A future observer with the right equipment might still identify it as the old telescope. It would not be taking data, but it would still carry the shape of its purpose, like an abandoned weather station still pointing its instruments at the sky, long after the last report. Over thousands of years, the story becomes less neat. Webb would experience sunlight continuously or periodically, depending on its orientation and orbit. The pressure of sunlight is tiny, but Webb has a large sunshield, and large thin surfaces can feel that pressure more than compact objects do. During the active mission, engineers account for this and use attitude control and momentum management. After the mission, sunlight becomes one more quiet influence on Webb's path and rotation. The push is not strong in the everyday sense. It would not shove Webb around like wind pushing an umbrella on a stormy street. But given enough time, even tiny pushes can matter, especially for an object with broad reflective surfaces. That is one of the useful habits of thinking about long times. A force can be too small to notice in an hour and important across centuries. A small leak can empty a tank. A tiny plant root can crack stone. A faint push from sunlight can alter the attitude and orbit of a light broad object. Webb was designed to manage these effects while alive. Afterward, it would simply experience them. The sun shield that once protected the telescope would become part of what makes its long-term drift complicated. Webb is not a dense round rock. It is an awkward shape by celestial standards, broad, folded-looking, reflective, and uneven. Space is very good at turning awkward shapes into interesting orbital math. Micrometeoroids would also become part of the slow future. A telescope in space is never completely alone. Dust grains and small particles move through the solar system at high speeds. During Webb's active life, impacts are expected and monitored when possible. The telescope was designed with this environment in mind, but over millions of years the number of encounters increases. Most particles would be tiny, many might do little. Some could make holes in the sun shield, some could chip mirror surfaces. A larger one, if chance delivered it, could break parts of the structure. Space is mostly empty, which helps Webb survive. But mostly empty is not the same as perfectly empty, and millions of years gives chance a very long schedule. The sun shield would probably be one of the first parts to show serious long-term wear, simply because it is so large and so thin. During the mission, that thinness is brilliant engineering. It reduces mass and allows the layers to block and radiate heat efficiently. As a relic, it becomes more vulnerable. A broad, thin sheet presents a large target. Holes, tears, and curling edges could accumulate. Layers could separate or become ragged. Some sections might remain attached for a very long time. Others might eventually rip free after impacts or thermal stress. If small pieces break away, they would become their own tiny artificial objects in solar orbit, each following a slightly different path. Webb's future might slowly stop being one object and become a small family of fragments. The mirror segments might survive longer in recognizable form. They are sturdier than the sun shield and made for stability. But their precision would no longer matter. During the mission, each segment must be aligned to work as part of one large mirror. After the mission, alignment can drift, actuators can fail, supports can be stressed, and impacts can change surfaces. A gold-coated segment floating in sunlight might still be physically impressive, but it would no longer be part of an observing system. A mirror without pointing, cooling, instruments and communication is just a mirror. Perhaps a very expensive mirror, but still not a telescope in the working sense. It would reflect sunlight, warm and cool, and continue around the sun. Millions of years are long enough for Webb's orbit to be changed by planetary perturbations. That phrase sounds tidy, but it means the planets can tug at Webb over time. Earth would remain important if Webb's orbit kept it near Earth's path. Venus, Mars, and especially Jupiter could matter depending on the shape of the orbit. Jupiter is massive enough to reshape the futures of small bodies across the solar system. Many comets and asteroids have had their paths changed by close approaches to planets. Webb would be much smaller than any planet, and would respond to those tugs as any small object does. A close enough encounter could alter its orbit significantly. Not necessarily a collision, but a change of path. It might become more elongated. It might move farther from Earth's orbit. It might enter a resonance, a repeating gravitational rhythm with a planet. Or it might be nudged into a path that becomes unstable over longer times. This is where exact prediction becomes difficult. For years and decades, engineers can track spacecraft very well. For centuries, if records and observations continue, the orbit could still be refined. For millions of years, tiny uncertainties grow. A small difference in a close approach can become a large difference later. A little change in rotation can affect how sunlight pressure acts. A fragment breaking off can slightly change the main body. A micrometeoroid impact can alter spin. None of these needs to be dramatic by itself. Together, over deep time, they make the exact path impossible to state with confidence. We can say Webb would likely continue as a solar orbiting object for a very long time after its mission, unless it is intentionally moved, captured, collided, or scattered. But we cannot honestly give it a neat address in the year 1 million, let alone 1 trillion. There is a familiar feeling to this if you have ever tried to predict where a plastic bag will blow across a car park on a windy day. For the first second, you may do well. After 10 seconds, you are less sure. After a minute, a small swirl of air, a curb, or a passing bicycle can change everything. Webb's case is more orderly because orbital mechanics is not random wind. But over long times, small uncertainties still spread. The solar system is stable in the broad sense, but small objects can have complicated histories. They can be nudged, scattered, trapped, or lost into new paths. Webb would become part of that small object population, not by design, but by retirement. If Webb's orbit remains near Earth's, one possible long-term outcome is that it has repeated distant encounters with the Earth-Moon system. Most would not be especially close. Space gives plenty of room to miss, but repeated opportunities matter. A close pass by Earth or the Moon could change the orbit more strongly than ordinary distant tugs. It could send Webb into a slightly different solar orbit. In some versions of the future, it might eventually enter a path that crosses Earth's orbit in a way that could lead to re-entry or impact. Though this would not be the simple expected outcome from L2 retirement. In other versions, it might be pushed farther away, becoming a faint artificial asteroid with no close return for vast stretches of time. The range of possibilities widens as the calendar grows. Another possibility is that Webb remains intact enough to be identified for a very long period but becomes difficult to find. Tracking an object requires observations, records, and interest. If future civilizations keep excellent catalogues, Webb's orbit might remain known. If records are lost or attention shifts, it could become an anonymous moving point. It would still exist, but no one would know exactly which faint object it was. There is something oddly practical about that. The universe does not label artifacts for us. We have to do the labeling ourselves, and we have to keep doing it. A silent telescope can be lost not because it hides, but because no one keeps looking in the right way. For millions of years, Webb would also be living through changes on Earth that are enormous compared with human history, but small compared with the Sun's lifetime. Continents would shift, coastlines would change, species would evolve, ice ages might come and go. The Moon would drift a little farther away. Earth's rotation would slowly change. Human languages, if humans are still here, would be unrecognizable to us. The launch date of Webb, December 25, 2021, might become a historical detail preserved in archives, or it might become as distant and uncertain as the first use of a stone tool is to us now. Meanwhile, the object itself could still be circling the Sun, no longer part of daily science, but still part of the physical solar system. It is useful to compare this with objects on Earth. A building left alone for 1,000 years usually changes greatly, because Earth is busy. Rain, wind, plants, microbes, ice, heat, and people work on it. A shipwreck becomes reef, rust, and sediment. A monument erodes. A book decays unless protected. Space is different. It lacks weather in the ordinary sense. No rain falls on Webb. No roots grow through its structure. No ocean rusts it in the familiar way. That gives space artifacts a chance to survive far longer than similar objects on Earth. But space has its own weather. Radiation, charged particles, ultraviolet light, thermal cycling, dust impacts, and gravitational changes. It is not gentle. It is simply patient in a different style. If Webb breaks into pieces, those pieces would not necessarily stay together. Slight differences in speed, shape, and sunlight pressure would separate them over time. A mirror segment, a piece of shield, a structural strut, and a small panel might each follow its own orbit. At first, they would stay near the original path. Later, they could spread into a loose stream of debris. Over enough time, Webb might become less like a single relic and more like a thin trail of artificial fragments sharing a common origin. Natural comets do something similar when they shed dust along their orbits, leaving streams that planets can later pass through as meteor showers. Webb would not create a visible meteor shower unless fragments encountered an atmosphere, but the idea of a trail is helpful. A once unified object can become a family of related paths. Would any of those pieces ever leave the solar system? It is possible in principle, but not the automatic result. To escape the Sun, an object needs enough speed relative to the Sun, or a strong gravitational assist from a planet or passing star. Webb near L2 does not begin as an interstellar probe. It was not launched onto an escape path like Voyager. It was placed in a solar orbit tied to Earth's motion. Without a major encounter or intentional push, it would remain bound to the Sun. Over millions of years, planetary interactions could change the orbit, but ejection is not something we should assume. More likely, at least across the earlier long future, Webb stays in the solar system as a human-made minor object, altered but still gravitationally part of the Sun's family. The Sun itself would remain almost familiar over millions of years. It would be a little older, slightly changed, but not yet the red giant it will become much later. Millions of years sound enormous to us, and they are enormous for biology, geology, and civilization. But for a star like the Sun, 1,000,000 years is a short interval. Even 10 million years is not much compared with the Sun's total lifetime. So during this stage of Webb's drift, the solar system is still broadly the solar system we know. The planets are still there, the Sun still shines, Earth still orbits. Webb, if it survives, is not yet watching the death of the Sun. It is simply getting older in a system that still looks, in its major layout, recognizable. That makes this stage of the story strangely quiet. It is not the age of cosmic endings yet. It is not the trillion-year future. It is the long middle after usefulness, and before true deep time has done its largest work. Webb becomes a silent small body in solar orbit. It may tumble, it may fragment, it may be tracked or forgotten, it may stay near Earth's path or be nudged elsewhere. It may survive in recognizable pieces because space is empty, or be gradually damaged because space is not empty enough. It is neither alive as a mission nor gone as matter. It is in the long after. This long after matters because it reminds us that the end of communication is not the end of an object's history. When a signal stops, our story with a spacecraft changes, but the spacecraft's physical story continues. The last data packet is not the last orbit. The last command is not the last motion. Webb's mission may last decades, but its body could remain for far longer, becoming part of the solar system's slow inventory. There is a difference between being useful, being remembered, being intact, and simply being. Webb may pass through all of those states, and maybe that is the calmest way to imagine it. Not as a dead machine abandoned in a dramatic darkness, but as a former observatory becoming a small solar orbiting relic. It circles because it was already circling. It drifts because no one is correcting the drift anymore. It ages because all materials age. It survives for a while because space is wide. It changes because space is not perfectly empty. Each orbit carries it through another year. Each century adds small effects. Each millennium makes its original mission more distant. Across millions of years, Webb becomes less connected to the people who launched it, and more connected to the larger mechanics of the solar system. For us, millions of years are almost impossible to hold in the mind. They are longer than recorded history by a factor so large it becomes silly. They are longer than the existence of our species as we know it. But for Webb's matter, millions of years are just many trips around the Sun. Orbit after orbit, with no need to count them. If it remains near 1-year periods, 1,000,000 years could mean around 1,000,000 circuits. If its orbit changes, the number differs, but the point is the repetition. Around the Sun, again and again, no applause, no scheduled observations, no calibration files, no images released to the public. Just motion. By the time we let the clock run from millions of years to billions, James Webb's story begins to pass from spacecraft history into solar system history. In the earlier stretch, Webb may be imagined as a silent artificial object drifting around the Sun, slowly aging, perhaps still partly recognizable, perhaps already becoming fragments. But after enough time passes, the question is no longer only what happens to Webb, it becomes what happens to the whole stage on which Webb is moving. The Sun changes, Earth changes, the Moon changes, the planets shift outward. The comfortable arrangement of the solar system, the one we learn in school with neat circles and familiar names, becomes less familiar. And if Webb, or any piece of web, is still there, it must go through those changes too. Right now, the solar system feels steady because human lives are short. The Sun rises every day. Earth follows its orbit. The Moon returns through its phases. Even the planets, with all their wandering across the sky, come back in predictable patterns. This is one of the reasons the sky has always felt like a source of order. It moves, yes, but it moves with rules. You can build calendars from it. You can navigate by it. You can look at the Moon and know roughly where you are in the month. But this steadiness is only local. It is steadiness at our scale. Over billions of years, the solar system is not frozen. It is an aging system built around an aging star. The Sun is the center of this future. Everything else in the solar system is living under its long schedule. Today, the Sun is a main sequence star steadily fusing hydrogen into helium in its core. It has been doing this for about 4.6 billion years, and it has enough fuel to continue in this familiar mode for several billion years more. During that time, it will not remain exactly the same. It gradually grows brighter. Very slowly, over hundreds of millions and billions of years, the amount of energy reaching Earth increases. This matters before the dramatic red giant stage even begins. Long before the Sun swells into something enormous, Earth's climate would be pushed beyond the comfortable range we know. The future Earth does not wait peacefully until the final act. Its difficulties begin much earlier. That is a point worth keeping clear. When people hear that the Sun will become a red giant in about 5 or 6 billion years, it is easy to imagine Earth remaining more or less normal until then, with oceans, clouds, birds, traffic, and someone still wondering whether they left the oven on. But the Sun's brightness changes gradually. A brighter Sun means more heating. Over very long times, this can destabilize Earth's climate. Oceans could evaporate. Carbon dioxide cycles could fail. The surface could become uninhabitable long before the Sun physically expands near Earth's orbit. So the familiar living Earth, blue and wet and full of noise, does not last all the way to the red giant Sun. The planet may remain, but the world we know would not. The Moon also changes during this time, though in a quieter way. Today it is slowly moving away from Earth because of tidal interactions. The Moon raises tides on Earth, and because Earth rotates faster than the Moon orbits, those tidal bulges pull slightly ahead of the Moon. Their gravity gives the Moon a small boost, moving it outward, while Earth's rotation gradually slows. This is happening now at about 4 centimeters per year, which sounds tiny. 4 centimeters is the kind of distance you might ignore when moving a chair, but over millions of years it adds up. Over hundreds of millions it matters more. The Moon becomes farther away in the sky, and Earth's day grows longer. Not by much from one generation to the next, but steadily in the patient language of tides. If the Sun's future did not interfere, the Earth and Moon might eventually settle into a double tidal lock, where Earth always shows the same face to the Moon, just as the Moon already shows the same face to Earth. But the Sun's evolution does interfere. The Earth-Moon system does not get a peaceful, unlimited future in which tides do their slow work for tens of billions of years. The Sun will change the environment long before that simple tidal endpoint is reached. This is one reason far future astronomy is full of careful phrases. We can describe processes, but the processes do not always get to finish before another, larger process interrupts them. The Moon is moving away, yes. Earth is slowing down, yes. But the red giant Sun will rewrite the situation before that quiet dance reaches its theoretical ending. When the Sun begins to leave its main sequence life, it will run out of hydrogen fuel in its core. The balance that has held it steady will change. Gravity will compress the core while hydrogen fusion continues in a shell around it. The outer layers will expand. The Sun will grow much larger and brighter. Mercury will not survive this phase. Venus is also expected to be swallowed. Earth's fate is more complicated and still discussed, because two effects compete. As the Sun expands, its outer layers may reach or come very close to Earth's orbit, and tidal drag could pull Earth inward. But as the Sun loses mass, its gravitational grip weakens, causing planetary orbits to expand. It is like a dangerous negotiation between being pushed outward by a weakening Sun and being dragged inward by a swelling one. The result is not a comfortable future either way. Even if Earth avoids complete engulfment, it would be a burned, altered world, stripped of habitability. For the Moon, Earth's fate matters directly. If Earth is swallowed or destroyed, the Moon's story changes with it. The Moon is bound to Earth now, but in a red giant future, with Earth heated, possibly engulfed, and influenced by the Sun's expanding outer layers and mass loss, the neat Earth-Moon pair may not survive as we know it. If Earth is engulfed, the Moon may also be lost or severely disturbed. If Earth somehow survives physically, the Moon's orbit could be altered by the changed gravitational environment and by Earth's own changes. The pair would not simply continue as a quiet blue planet and grey companion under a larger orange sun. By then, Earth would be unrecognisable, and the Moon would no longer be the familiar lamp of human evenings. This matters for Webb because Webb's early afterlife may keep it near Earth's general orbital neighbourhood, depending on its final path. If a remnant of Webb is still moving in a solar orbit after billions of years, then the red giant Sun becomes a serious event in its history. A small artificial object in the inner solar system would be exposed to a much brighter, larger, more unstable Sun. The thin remains of the sunshield, if any survived, would not be helped by that. Metals and coatings would experience extreme heating depending on distance and orbit. Radiation pressure and solar wind conditions would change. If Webb's remnant remained near an orbit similar to Earth's, the future red giant phase could damage it, alter it, or possibly engulf it depending on the exact orbit and the size of the Sun at that stage. If earlier gravitational nudges had moved it farther out, it might avoid the worst. Once again, Webb's exact fate depends on details that become uncertain over long time. The outer planets have a different kind of future. Jupiter, Saturn, Uranus and Neptune are far enough from the Sun that they are not swallowed by the red giant. They will be heated more strongly for a while, but they are not sitting in the danger zone like Mercury, Venus and possibly Earth. As the Sun loses mass, the gravitational hold on the surviving planets weakens. Their orbits expand. This is an important detail. When a star loses mass slowly compared with the orbital periods of its planets, the planets do not usually fly away instantly. Instead, their orbits grow larger. A planet that once circled closer moves farther out. In broad terms, if the Sun loses roughly half its mass, surviving planets can end up at roughly larger distances than before. The solar system spreads out. Imagine then a future solar system after the Sun has shed its outer layers. The centre is no longer the bright yellow sun we know. It is a white dwarf, the exposed remnant of the sun's core, about Earth-sized but with a large fraction of the sun's former mass packed into it. Around it, any surviving planets orbit farther away than they once did. Jupiter still exists, likely farther out. Saturn, Uranus, and Neptune still travel in widened paths. The inner solar system may be emptied or ruined. Earth may be gone, or it may be a scorched remnant if it somehow escaped destruction. The moon's familiar role may be ended. The warm daylight that shaped life on Earth is replaced by the fading glow of a stellar remnant. This is the solar system after the sun's main life is over. Not destroyed completely, but transformed. It is important not to picture a supernova, because the sun is not massive enough for that. It will not explode like a massive star. It will swell, shed its outer layers, and leave behind a white dwarf. For a time, those shed layers may form a glowing shell, a planetary nebula-like structure, though how dramatic or visible the sun's own final display would be is a matter of modelling. But the broad ending is clear. The sun becomes a white dwarf and begins the long process of cooling. By 1 trillion years from now, that white dwarf would be ancient. 1 trillion years is not just the end of the sun's red giant phase, it is far beyond it. The red giant phase will have passed. The shedding of outer layers will have passed. The white dwarf stage will have been underway for an enormous length of time. The sun's remnant will be faint, cold compared with its youth, and no longer powered by fusion. It will be radiating leftover heat into space, cooling slowly. Whether we call it a very cold white dwarf or imagine it approaching the idea of a black dwarf depends on details of white dwarf cooling. But the essential point for this story is simple enough. The sun will no longer be a sun in the familiar sense. It will not provide warm daylight. It will not define a habitable zone like the one Earth once enjoyed. It will be a cooling ember at the centre of a much older system. The planets that survive around it would orbit in darkness compared with today. They would receive far less energy. Jupiter would still be massive, still able to shape the paths of smaller bodies. Saturn, Uranus and Neptune may remain, unless later gravitational disturbances change their futures. Their moons may still exist, though also altered by time, impacts, internal cooling, and the loss of sunlight. The outer solar system would be colder and dimmer. The small body populations, asteroids, comets, fragments, and dust would be changed by billions of years of collisions and gravitational scattering. Some objects would have been ejected. Some would have fallen inward. Some would remain in distant reservoirs. The solar system would not be gone, but it would be old in a way no landscape on Earth can help us imagine. Where is Earth in that trillion-year picture? The honest answer is that Earth may not exist as a planet in any familiar way. Many models suggest Earth is unlikely to remain intact through the sun's red giant evolution, though uncertainty remains in the details. If it is engulfed, then the Earth as a separate planet is gone, its material mixed, heated, dragged, and redistributed in the sun's outer layers or later debris. If it survives physically, it would be a dead, altered remnant orbiting farther from the white dwarf sun, stripped of oceans, air, and life as we know it. It would not be home, it would not be blue. It would not be a world of clouds and forests. It would be a planetary corpse if it exists at all. That sounds harsh, but it is only harsh because we know what Earth is now. And the moon, if it survives separately, would also be changed. Without a living Earth, without oceans raising tides, without the same Earth-Moon relationship, the familiar monthly rhythm is gone. If Earth is engulfed, the moon may be engulfed or destabilized too. If the pair survives in some form, the moon may orbit a ruined Earth at a different distance, under a faint white dwarf sun. The night sky from such a world, if there were anyone to stand there, would not be a night sky for calendars, tides, and bedtime windows. It would be a museum of absence. But of course, there may be no one there to see it, and no atmosphere left to make a sky in the way we understand one. A Webb remnant, meanwhile, if it has survived the red giant phase and the billions of years afterward, would be part of the small debris population orbiting the white dwarf Sun. The Sun's mass loss would have expanded its orbit if the mass loss happened slowly while the object remained bound. If Webb had been near Earth-like distances, that expansion might have moved it outward. If it had been scattered earlier, its path could be very different. If it passed too close during the red giant phase, it might have been damaged or swallowed. If it fragmented, different pieces might follow different futures. At 1 trillion years, it is probably safer to imagine not a pristine telescope, but possible remnants. A mirror segment, a lump of structure, a small piece of gold-coated material, a fragment of beryllium, or perhaps only atoms dispersed into other material. The most remarkable thing about this stage is that the solar system still may have structure. The Sun is no longer shining as it does now, but gravity remains. A white dwarf still has mass. Planets can still orbit it. Small bodies can still move under its influence. Webb's atoms, if still nearby, still obey the same gravitational rules. Deep time does not remove physics, it removes familiarity. The clock runs so far that names like Earth, Moon, and Sun become less like everyday things and more like ancient phases of objects that changed beyond recognition. 1 trillion years also places the solar system inside a changed galaxy. The Milky Way and Andromeda are expected to merge long before then, reshaping the local galactic environment. The Sun's remnant would no longer be one star among the same spiral pattern we see today. It would be part of a larger merged galaxy, moving among old stars, red dwarfs, white dwarfs, neutron stars, black holes, and the fading remains of earlier generations. Stellar encounters over such long periods may disturb distant comets and small bodies. Close passes by other stars, rare but meaningful over long times, could perturb the outer parts of the system. If a Webb fragment remains weakly bound on a distant orbit, such encounters could matter. It might be nudged inward, pushed outward, or even ejected into interstellar space. 1 trillion years gives the galaxy many chances to interfere. This is why there is no single clean map for Webb at 1 trillion years. The solar system itself will be too changed, and the small object's history too sensitive to earlier events. But we can say what the environment would be like. No warm sun, no normal Earth, no familiar moonlit nights, no active Webb. The centre of the system would be a cold stellar remnant. The surviving planets would be farther away and colder. The inner solar system would be stripped, disrupted, or emptied. Artificial relics from human spaceflight, if any remain, would be indistinguishable from small debris unless someone still knew how to identify them. And yet, there is still a quiet connection between that future and now. The same sun that warms your skin today will become that white dwarf. The same earth under your feet may be gone or altered into something unrecognizable. The same moon that raises tides tonight is slowly changing its distance even as we speak. The same Webb that once watched early galaxies may, in some form, pass through the sun's aging and become part of that ancient system. Nothing here is separate. A telescope launched in the 21st century, a moon formed billions of years ago, an Earth that grew oceans, and a sun burning hydrogen in its core are all temporary arrangements in a much longer chain. This does not make the present smaller, it makes it more specific. We happen to live in the era when the sun is stable, Earth is habitable, the moon is close enough to shape tides, and Webb is still recent enough that we know its name. We live during the window when the solar system is not young, but not yet old in the red giant sense. We live while telescopes can be launched to L2, while Earth can receive their signals, while scientists can compare models to data, while someone can ask where a machine will be in 1 trillion years and still mean it with a straight face. That is a very particular moment to occupy. So as we carry Webb forward in our imagination through the future solar system, we have to let go of the idea that the background stays still. Webb does not drift through a permanent arrangement of planets. It drifts through a system that ages around it. First the sun remains familiar, then brighter, then unstable, then huge, then stripped, then white and cooling. Earth moves from living world to uninhabitable world, and perhaps to destroyed material or barren remnant. The moon moves outward for as long as the Earth-Moon system allows, then faces whatever the sun's transformation brings. The outer planets retreat into wider, colder orbits. Small bodies scatter, collide, and sometimes escape. The whole solar system stretches, dims, and quiets. In that trillion-year stillness, if any piece of Webb remains, it would no longer belong to astronomy as a working tool. It would belong to the archaeology of matter. Perhaps it would be a small dark fragment circling a white dwarf sun. Perhaps it would have been shattered into dust long before. Perhaps it would be far from the sun, nudged outward by planetary encounters or a passing star. Perhaps it would be gone from the solar system entirely. But wherever its material is, it would have travelled through a future in which the objects closest to us now, Earth, the Moon and the Sun, have all changed beyond easy recognition. And that is the doorway into the next question. Because once the solar system has aged so completely, once Webb is no longer likely to be a telescope in any practical sense, we have to ask what could remain of it at all. When we're asking whether James Webb still exists as metal, dust or memory, we have moved beyond the normal language of missions. We're no longer asking whether the telescope can point at a galaxy, whether its instruments can measure the atmosphere of an exoplanet, whether its sun shield can keep the cold side cold, or whether its radio signal can reach Earth. Those questions belong to the working life of Webb, the part of the story filled with schedules, data, calibration, proposals, and scientists waiting for results. Here, we're asking something stranger and quieter. After the mission ends, after millions of years of drifting, after the solar system begins to age around it, what remains of the object itself? Is Webb still a telescope? Is it still metal? Has it become dust? Or is its most lasting form not physical at all, but memory? At first, the answer seems simple. Webb is made of materials, and materials do not vanish just because a mission stops. Its mirror segments are made from beryllium, chosen because it is strong, light, and able to behave well at the very cold temperatures Webb needs. Those segments are coated with an extremely thin layer of gold, not because the telescope wanted to look glamorous, though it did accidentally become one of the most glamorous machines ever launched, but because gold is excellent at reflecting infrared light. Its sunshield is made from thin Kapton film, arranged in 5 broad layers, each layer helping to block and radiate heat so the telescope side can stay cold. Its structure includes metals, composites, electronics, propellant tanks, cables, sensors, instruments, and many pieces whose names sound less like astronomy and more like the contents of a very serious engineering cupboard. These things are real. They have mass. They are not ideas. So in one sense, yes, Webb continues as material after its mission ends. But existence is not one simple thing. A telescope can exist as a working instrument. It can exist as an intact but silent machine. It can exist as fragments. It can exist as scattered atoms. It can exist in photographs, archives, papers, memories, and stories. These are different kinds of survival, and Webb may pass through several of them. Today, Webb exists as a working observatory, or at least in our present era of discussion, it belongs to that active identity. It is a system. Mirror, instruments, sun shield, spacecraft, orbit, commands, power, data, and people. Remove enough of those connections and the same physical object becomes something else. It is still Webb in one way, but not in another. A violin without strings is still the violin's body, but it is no longer making music. A lighthouse without a lamp is still a tower, but it is no longer guiding ships. A space telescope without pointing, cooling, instruments, and communication is still a spacecraft, but the observing life has ended. For a while after its mission, Webb may remain mostly intact. Space does not have rain, wind, moss, salt water, insects or people leaning on things they should not lean on. On Earth, delicate machines decay quickly unless protected. Rust spreads. Plastic becomes brittle. Wood rots. Paint flakes. Dust settles. Water gets in because water has a remarkable talent for getting in. Space lacks many of those familiar agents of decay. A spacecraft can remain recognizable for far longer than a similar object left outdoors on Earth. That is one reason the footprints and hardware on the Moon may last for such long times. Without weather, change becomes slower, but slower is not the same as never. Space has its own version of weather, and it is not sentimental. Webb would be exposed to radiation from the Sun and from beyond the solar system. Charged particles can change materials. Ultraviolet light can damage surfaces. Cosmic rays can pass through and disturb atoms. Temperature changes can make materials expand and contract. Sunlight can push, faintly but continuously. Dust grains and micrometeoroids can strike at high speed. These processes may be quiet, but they do not require hurry. If Webb is drifting for thousands, millions, or billions of years, tiny effects have time to become history. The telescope was designed to survive the space environment for its mission lifetime and with luck beyond it. It was not designed to remain pristine for 1 trillion years. That would be an unreasonable request, even by the standards of people who built a folding golden telescope and sent it beyond the Moon. The sun shield is likely the most fragile-looking part of Webb's long future. During the mission, it is a triumph of design, a huge layered shield that makes infrared astronomy possible. As a relic, it becomes a wide target. It is thin, broad, and exposed. Tiny impacts may punch through, larger impacts may tear, thermal stresses may distort it, sections may curl, stiffen, split, or detach. If a piece of the shield breaks away, it does not fall down. It becomes a new object in orbit, with a slightly different speed, shape, and response to sunlight. Because it is thin and light, radiation pressure from sunlight may affect it more strongly than denser pieces. Over time, fragments of shield could spread away from the main body like flakes from an old sail. They would not sparkle in some dramatic cloud visible from Earth. They would simply join the faint population of small artificial debris moving according to gravity and light. The mirror segments are sturdier, but they are not immortal either. Beryllium is strong and light, which made it suitable for Webb's mirror, and the gold coating helps reflect infrared light. But a mirror's scientific value depends on more than its material. It depends on smoothness, shape, alignment, temperature, and integration with the rest of the observatory. A micrometeoroid impact can leave a crater. Many impacts can roughen surfaces. A larger collision could crack, chip, or detach a segment. Over enough time, the mirror could lose its precise identity as a mirror, becoming a damaged reflective surface, then a fragment, then perhaps smaller fragments. If one segment survived alone for billions of years, would it still be Webb? It would be part of Webb. It would carry Webb's material history. But it would not be the telescope in the way we mean when we say James Webb looked into the early universe. This is where identity becomes slippery. Suppose in the far future a single gold-coated beryllium segment survives, orbiting the Sun's white dwarf remnant. It has holes, scratches, and perhaps no longer shines the way it once did. The sun shield is gone. The instruments are gone. The spacecraft body is gone. Is that still James Webb? In museum language, yes, it could be a surviving piece of the James Webb Space Telescope. In physical language, it is a piece of material with a history. In emotional language, it might feel like a relic, the way a piece of an ancient ship can stand for the whole voyage. But the complete object would be gone. The identity would have narrowed from telescope to artifact to fragment. Now imagine the fragment is broken further. A small chip of beryllium, a fleck of gold, a torn strip of capton, a screw, a sliver of insulation, a shard of structure. Each part once belonged to Webb. Each part still carries atoms that were assembled by human design. But at some point, the name Webb becomes more like ancestry than identity. The material came from Webb, but it no longer is Webb in the ordinary sense. This happens on Earth too. A building becomes rubble. Rubble becomes sediment. Sediment becomes part of a landscape. We do not point to a grain of sand and call it the castle, though the grain may once have been part of the castle wall. Matter remembers nothing in itself. Memory requires minds, records, or patterns that survive. Dust is a possible end for Webb's material, but dust in space is not the same as dust under a bed. Under a bed, dust is a domestic accusation. In space, dust is part of cosmic recycling. Tiny grains can orbit the sun, be pushed by radiation pressure, spiral slowly due to interactions with sunlight, collide with other grains, or be swept into planets, moons, or the sun. Some dust grains become meteors when they enter an atmosphere. Others remain for long periods. If Webb becomes dust, its particles may spread into many paths. Some may orbit the sun for ages, some may be perturbed by planets, some may be blown outward if small enough, some may be incorporated into other bodies. The telescope's material would no longer have one location, it would become distributed. Over billions of years, the sun's red giant phase adds another transformation. If Webb or its fragments are still in the inner solar system, the swelling and brightening sun may heat them severely, alter their surfaces, or engulf them. Captain fragments would not be expected to survive such extreme heating in any recognizable way if they passed too close. Metals and beryllium might survive as vaporized, melted, chemically altered, or redistributed material depending on circumstances. Gold has a high resistance to many forms of chemical change, but it is not a magic shield against the future of a star. A thin coating on a mirror segment is especially vulnerable to being damaged, stripped, mixed, or melted if conditions become extreme enough. If Webb has been moved or scattered farther out before the red giant phase, some pieces might avoid the worst heating. If not, the sun's transformation could erase Webb as a recognizable object long before 1 trillion years. If pieces survive the red giant era, they would orbit a white dwarf sun in a colder, dimmer solar system. Around white dwarfs, astronomers have found evidence that planetary debris can be torn apart and sometimes fall onto the star, polluting its atmosphere with heavy elements. That gives us a real astronomical clue that small bodies around old stellar remnants can still have active, messy futures. A surviving Webb fragment around the sun's white dwarf remnant would not be protected just because it had once been important. If its orbit were disturbed by planets or other bodies, it could be sent inward, perhaps close enough to be heated, broken apart by tides, or eventually accreted onto the white dwarf. In that case, Webb's atoms might become part of the outer layers of the dead sun, a strangely intimate ending for a telescope that once used sunlight as both power source and threat. Another possibility is ejection. Over very long times, gravitational encounters can send small objects out of the solar system. A close pass by a planet, especially a giant planet, can change a small object's orbit drastically. A passing star can disturb distant debris. The merged future galaxy will contain many old stars moving through space, and rare close encounters can reshape the outer regions of planetary systems. If Webb or its fragments are scattered outward and then nudged by stellar encounters, some material might escape the sun entirely. In that version, Webb becomes interstellar debris, no longer bound to the sun, drifting between stars as an artificial grain or fragment. It would be a cousin, in a strange way, to the Voyager spacecraft, though Webb was not built for that path and would not carry a record meant for anyone to find. If a Webb fragment entered interstellar space, it could last a very long time, especially if it were dense and compact. Interstellar space is thin, collisions are rare. But rare is not never, and 1 trillion years is very generous to rare events. Cosmic rays would continue to alter materials. Dust impacts would occur occasionally. Encounters with gas clouds might erode surfaces. A fragment might remain recognizable in material composition but not in shape. A gold atom that once helped reflect infrared light could end up in a completely different environment, perhaps in interstellar dust, perhaps in a future star-forming cloud if the galaxy still contains enough gas in some region. Though 1 trillion years from now, star formation will be far less abundant than it is today. The atom does not know it was once part of Webb. Only a memory system could know that. Memory may outlast the object in some ways, but memory has its own fragility. Webb exists today not only as hardware, but as data, images, engineering records, scientific papers, mission logs, computer files, news articles, documentaries, educational material, and the personal memories of people who watched it launch, unfold, align, and begin science. This is another form of Webb. The telescope is not only the object near L2, it is the knowledge it produced. It is the deep field images that altered how people imagined the early universe. It is the spectra that reveal molecules in distant atmospheres. It is the engineering lessons that help design future telescopes. It is the fact that a species on Earth proved it could unfold a cold infrared observatory in deep space and use it to study light older than the solar system. In the near future, this memory may be Webb's strongest survival. Long after the telescope stops working, its data archive may remain scientifically useful. Astronomers may return to old observations with better models and new questions. Measurements that seemed ordinary at first may become important later. Future instruments may compare their results with Webb's early infrared view of the universe. The telescope may stop gathering new photons, but the photons already gathered will remain in data form. This is a beautiful thing about observatories. They do not only make discoveries while they are alive, they leave archives that can keep discovering with us, if we keep reading them. But 1 trillion years is a harsh timescale for memory. Human archives do not have a natural million-year guarantee, let alone a trillion-year one. Stone inscriptions can last thousands of years under good conditions. Digital storage can fail in decades without maintenance. Paper burns, rots and fades. Languages change. Civilizations rise and fall. Even if humanity or its descendants survive for a very long time, maintaining a continuous memory for 1 trillion years would require a chain of preservation far beyond anything we have ever achieved. It is not impossible in the broadest speculative sense, especially if future intelligence becomes very good at archiving, copying and transmitting knowledge. But it is not something we can assume. Memory, like a spacecraft, needs maintenance. There is a difference, though, between memory in a mind and consequence in the universe. Even if no one remembers Webb's name in 1 trillion years, the observations it made may have shaped later knowledge. A discovery can influence another discovery, which influences another, until the original source is forgotten but its effects remain. We do this all the time. Most of us use ideas whose first discoverers we cannot name. We live inside layers of inherited knowledge. Webb's data may help build theories, instruments, and decisions that continue forward long after the telescope itself is gone from common memory. In that sense, Webb might survive not as a remembered object, but as part of the intellectual ancestry of future science. There is also public memory, which is softer and less precise but still powerful. Webb is one of those missions that entered culture, not just astronomy. People saw the golden mirror, they saw the first images, they learned that looking far away can mean looking back in time. For many, Webb became a symbol of curiosity, patience, and the strange success of careful engineering. Symbols can last in altered forms, the details may blur, the numbers may be forgotten, the specific orbit may be simplified. But the idea of Webb, the telescope that looked into deep time, might persist in stories much longer than its hardware remains intact. Whether it persists for 1 trillion years is another matter. That is almost beyond storytelling itself. If future beings did find a surviving piece of Webb, memory and metal could meet again. Imagine a distant civilization, perhaps descended from us, perhaps something else entirely, discovering a small artificial fragment in orbit around the Sun's white dwarf remnant. They analyse it. They find refined beryllium, gold coating, manufactured structures, isotopic signatures, perhaps traces of design. If they also have archives, they might identify it. If not, they might infer that an earlier technological species built it. The fragment would become evidence, not just debris. A single piece of web could speak without transmitting, because its manufactured nature would be hard to mistake. It would say, in the silent language of artifacts, someone made this. But if no one finds it, does that kind of survival matter? I think it still does, though perhaps not in the way we usually mean. Meaning is relational. Webb meant something to the beings who built it and used it. It may mean something to future beings who study it or its data. To the universe without observers, it is matter in motion. That may sound cold, but it is also honest. The universe is not required to remember us. That is why memory feels precious. It is not guaranteed by physics. It is something living minds do for a while in small bright circles against an enormous background. So will James Webb still exist in 1 trillion years? The safest answer is that it almost certainly will not exist as the working telescope we know. It probably will not exist as a pristine golden observatory with its sunshield spread and its mirror intact, still recognisable in the same way we recognise it now. The timescale is too vast. The sun will have changed. The solar system will have changed. Micrometeoroids, radiation, thermal stress, gravitational encounters, stellar evolution, and chance will have had far too much time. It may exist as fragments. It may exist as dust. It may exist as atoms mixed into other objects or scattered into interstellar space. It may exist in data and records if those are preserved. It may exist as an influence on later knowledge even if its name is forgotten. Or it may survive in several of these forms at once. Some material here, some memory there, some consequence woven into future science. There is a gentle lesson in that. We often want survival to mean staying the same. We want the object preserved, the name remembered, the shape intact, the story unchanged. But the universe mostly preserves things by transforming them. Stars become white dwarfs, neutron stars, black holes, gas, dust, and new stars. Rocks become sand, sediment, planets, and vapour. Living things become memory, ancestry, soil, and chemistry. A telescope can become data, debris, legend, and atoms. Webb's far future is not one clean identity, but a widening set of transformations. And perhaps that is fitting for a telescope whose whole mission is about light transformed by time. Webb studies ancient starlight stretched by the expansion of the universe. It sees galaxies not as they are now, but as they were, because light takes time to travel. It turns photons into signals, signals into data, data into images, images into understanding, and understanding into new questions. Transformation is already built into its work. In the far future, Webb itself becomes the thing transformed. The observer becomes an object of deep time. For now, though, Webb is still recent enough that we can picture its shape. We can see the gold mirror in our minds. We can imagine the sunshield facing the warmth and the cold side turned toward the dark. That image will not last unchanged across 1 trillion years, but it does not need to. Its value is not that it remains forever. Its value is that it happened. A group of people on a small planet built a machine to see infrared light from the early universe, sent it beyond the moon, unfolded it in space, and listened. The machine will age, the materials will change, the memory may fade or be carried forward. But for a while, in this particular era of the solar system, Webb existed not just as metal, not just as captain and beryllium and gold, but as a working question aimed at the dark. Once 1 trillion years have passed, James Webb, if any part of it still exists at all, would not be drifting through the Milky Way as we know it tonight. That may be the first quiet adjustment we need to make in our minds. We often imagine the galaxy as a permanent background, a great fixed river of stars behind all the smaller stories of planets, telescopes, moons, and people. The Milky Way feels ancient, and it is ancient. It was already old before the sun formed, already full of stars before Earth had oceans, already turning through space before anything on our planet looked up and gave it a name. But ancient does not mean unchanging. A galaxy is not a painted ceiling. It is a moving system of stars, gas, dust, dark matter, star clusters, black holes, and smaller galaxies being pulled in, stretched out, and absorbed. It looks still because we are brief. Given enough time, even the Milky Way becomes a changing thing. So if some silent remnant of Webb survives into that far age, perhaps a mirror fragment, perhaps a lump of structure, perhaps only a few grains of altered material, it would belong to a galaxy that has been rearranged by gravity and time. The spiral arms we draw in diagrams may no longer be there in the same form. The bright young stars that mark the arms today may have died long before. The gas clouds that once made new stars may be depleted, heated, scattered, or locked away. The sky would not have the same familiar band of pale light that humans once saw from dark fields on Earth, and Earth itself may not be there to see it. The sun will have become a white dwarf, the moon's familiar rhythm may be gone, and the telescope that once used a cold mirror to study ancient galaxies would be, at most, an artifact moving through the remains of a much older stellar city. For a long time, astronomers expected that the Milky Way and Andromeda would collide and merge several billion years in the future. More recent work has made that future less certain in its exact timing and probability, because the motions and masses of the local group are complicated, and nearby galaxies such as the Large Magellanic Cloud and Triangulum can affect the outcome. That is a useful reminder that even galaxies, large as they are, do not give us perfect predictions just because we ask politely. The future of the Milky Way and Andromeda is not a simple train timetable. But over 1 trillion years, whether the Great Merger happens early, later, or in a more complicated sequence, the galaxy around the Sun's remnant will not be the same calm spiral we know today. Interactions, mergers with smaller galaxies, stellar aging, orbital mixing, and the gradual fading of star formation will all have done their work. If the Milky Way and Andromeda do merge, the event would not look like two solid objects smashing together. Galaxies are mostly empty space, which is a phrase that sounds simple until you remember it includes hundreds of billions of stars. When galaxies pass through one another, the stars themselves almost never collide directly because the distances between stars are so enormous. It is not like two swarms of bees meeting wing to wing. It is more like two vast clouds of points passing through each other, each point surrounded by huge emptiness. But gravity acts across the whole system. It stretches the galaxies into tidal tails. It disturbs stellar orbits. It compresses gas in some regions, possibly triggering bursts of star formation while gas remains available. It drags dark matter halos through each other. Over time, repeated passes can turn graceful spiral disks into a larger, more rounded system, often imagined as an elliptical-like galaxy. For Webb's remnant, if it still orbits the white dwarf sun, a galactic merger would not necessarily be a local disaster. Stars do not usually crash into planetary systems during such events. The distances are too large. The sun's remnant would simply be carried along as one small mass among many others, its orbit around the galactic centre altered by the changing gravitational field. But simply is doing a little too much work there. The night sky would be transformed. Stars from Andromeda would mix with stars from the Milky Way. The central black holes of the two galaxies may eventually spiral together and merge. The old disk structure could be disturbed or erased. The sun's remnant might be shifted into a new orbit within the merged galaxy, perhaps farther from the centre, perhaps in a halo-like region, depending on the details. And if Webb is still bound to the sun's remnant, it would be carried along, not because anyone planned it that way, but because gravity tends to bring its small companions with it. This is one of the humbling parts of the story. Webb was launched with precision. Its path to L2 was calculated. Its mirror was aligned with astonishing care. Its observations were scheduled in exacting detail. But in the far future, its movement through the galaxy would be part of events so large and slow that Webb's engineering purpose would no longer matter. A fragment of a telescope and a natural pebble in the same orbit would be treated alike. The merged galaxy would not know which one once observed early galaxies. It would not know that humans worried about mirror deployment, fuel margins, and micrometeoroids. It would simply carry the sun's remnant and whatever small debris remained with it through a reshaped gravitational field. By 1 trillion years, the universe would be much older than it is now, but not yet dead in the deepest possible sense. Many massive and sun-like stars would be long gone. Stars like the sun live for billions of years, not trillions. Their bright lives end as white dwarfs, neutron stars, or black holes depending on their mass, though the sun's own ending is the quiet white dwarf path. The galaxy at 1 trillion years would be rich in stellar remnants, white dwarfs cooling slowly, neutron stars spinning down, black holes sitting dark and less fed, and old red dwarfs still burning faintly. Red dwarfs are important here because they are the long sleepers of the stellar world. They are small, dim, and patient, burning their hydrogen so slowly that many can last for trillions of years. So the galaxy would not be completely dark at 1 trillion years. It would still contain living stars, especially the small red ones, shining modestly while the grander stars of earlier eras have already left the stage. That means a Webb fragment, if one could somehow look around, would not be in total blackness. There would still be stars. Not the same bright blue stars that mark active star-forming regions today, because those live fast and die young. Not many sun-like stars still shining in their middle lives, because those would mostly have aged into remnants, but red dwarfs would remain. Dim points, long-lived, steady in their quiet way. The galaxy would be older, redder, fainter, less full of new stellar birth. It would be a place where the universe has slowed down, not stopped. 1 trillion years is enough time for many familiar lights to go out, but not enough time for the last stars to vanish. Star formation itself would be greatly reduced. Today, galaxies form stars from cold gas clouds. The Milky Way still has such clouds, though far less star formation than some younger, more gas-rich galaxies. Over time, gas gets used up, heated, blown out by stellar feedback, locked into long-lived stars, or otherwise made unavailable. Mergers can stir gas and create bursts of star formation, but they also help consume and redistribute the supply. By 1 trillion years, ordinary star formation would likely be far rarer than it is now. The galaxy would be living largely on the stars it already made, especially the longest-lived ones. It is a little like a household late in the evening after the cooking is done. There may still be warmth in the kitchen, perhaps a few leftovers, perhaps a kettle still able to boil, but the busy making has passed. This matters for the feeling of the far future. Webb once studied star nurseries, dusty clouds where new stars were forming, glowing regions of gas, young galaxies crowded with early activity. Its instruments were designed to see through dust and measure the light of formation. But 1 trillion years later, the galaxy containing Webb's remains would be far less youthful. The grand cosmic fireworks would be quieter. There would be fewer bright young stars to illuminate gas clouds, fewer massive stars exploding as supernovae, fewer fresh heavy elements being scattered into new generations. The universe would still change, but with a slower pulse. If a piece of Webb remained near the sun's white dwarf, it would be orbiting a remnant among remnants. This is a strange phrase, but it fits. The sun's remnant would be an old white dwarf, cooling. Webb's remnant would be an old artificial fragment, damaged or altered. The galaxy around them would be filled with other old things, white dwarfs from stars like the sun, neutron stars from massive stellar deaths, black holes from the largest collapsed stars and from galactic centers. brown dwarfs that never became true stars. Planets, if they survive, orbiting faint suns or stellar corpses. It would be a universe where the early bright rush of star-making has become memory, written into the objects left behind. Would the Webb fragment still be bound to the Sun's remnant in such a galaxy? Possibly, if it survived the earlier solar system changes and avoided strong disturbances. A white dwarf can keep planets and small bodies in orbit if they are not swallowed, ejected, or destabilized. But 1 trillion years gives many chances for encounters. Passing stars, though still separated by large distances, can perturb outer orbits over time. In a merged galaxy, stellar motions may be rearranged. If the Sun's remnant ends up in a crowded region, close stellar passages become more likely than in a sparse outer halo. If it ends up far out, the system may be more isolated. A Webb fragment on a wide orbit would be easier to disturb than one close to the white dwarf. A close fragment might be more likely to survive gravitationally, but could face other risks, such as being drawn inward if its orbit is destabilized by leftover planets or debris. The possibilities multiply because the object is small and the timescale is huge. If Webb had already become dust before this era, the question changes. Dust grains do not have one simple story. Some spiral inward under subtle effects related to sunlight and radiation. Some are blown outward if small enough. Some collide and break. Some stick to larger bodies. Around a white dwarf, debris can be perturbed inward and torn apart, forming dusty disks. Astronomers have observed white dwarfs with signs of planetary material falling onto them, which tells us that old systems can remain active in small, messy ways. So if Webb has become dust, some of its atoms might be spread through the old solar system. Some might have fallen into the white dwarf's sun, some might be locked into a surviving planet or moon, and some might be drifting independently. At 1 trillion years, there may be no single Webb location. There may only be Webb ancestry distributed across matter. Memory faces an even more uncertain galaxy. Suppose some descendant civilization survives in some form. Perhaps not on Earth, because Earth's habitable future is short compared with these times, but around long-lived red dwarfs, artificial habitats, or other places we can only cautiously imagine. Would they remember Webb? Would the data survive? Would the launch, the mirror, the L2 orbit, the first images, the spectra of distant worlds still be known? 1 trillion years is such a long cultural interval that even the word remember begins to feel strained. But it's not impossible in principle that advanced descendants, if they exist and care to preserve knowledge, could maintain archives across deep time. They might treat Webb the way we treat the earlier stone tools or the first marks made by human hands, except with a gap vastly larger. They might know it as one of the early infrared observatories of a young technological species, an instrument from the brief habitable era of Earth. Or they might not remember at all. A civilization may not last. Archives may fail. Languages may transform beyond recognition. Data may be lost, copied incorrectly, buried under later knowledge, or intentionally forgotten. Even if intelligent life persists somewhere, it may not remain connected to Earth's history. It may have other concerns, other origins, other ways of understanding the past. In that case, Webb would be silent in a deeper sense. Not only no signal, but no memory. A relic without a label, a fragment without a story. A piece of manufactured material moving through an old galaxy where no one knows who manufactured it. There is a quiet sadness in that, but not a hopeless one. A forgotten thing was still once meaningful. Meaning does not require eternal audience. The first person to make a tool mattered, even if no one knows their name. A song sung once beside a fire mattered to the singer and listener, even if no recording exists. Webb mattered because it worked, because it revealed, because it changed what people knew while there were people to know it. Whether that memory survives 1 trillion years is another question. The value of a telescope is not reduced, because the future is long enough to forget it. In a galaxy changed beyond recognition, Webb's original surroundings would seem almost impossibly young. The Sun as a yellow star, Earth as a blue planet, the moonlighting oceans, astronomers planning observations from offices, rockets launching from Earth, radio antennas receiving data, people seeing the first deep images and sharing them across glowing screens, all of that would belong to a vanished era. The physical galaxy may still contain traces of those days, but not the context that made them ordinary. The solar system that launched Webb would be an old remnant system. The Milky Way, if merged, would be part of a larger structure. The familiar constellations would be long gone, not because the stars vanished all at once, but because stellar motions rearranged the sky over time. The patterns we name are temporary from the beginning. Orion, Cassiopeia, Scorpius, the Big Dipper, all are shapes made by our viewpoint in a particular era. 1 trillion years gives those shapes no chance of staying. If a future observer near another red dwarf looked toward the Sun's remnant, they might not see anything special. Just a faint white dwarf among many, perhaps with old planets or debris. Webb's remains, if nearby, would be too small and dark to notice without deliberate searching. The telescope that once made distant galaxies visible would itself be almost invisible. That reversal is worth sitting with for a moment. Webb was built to find faint things. In the far future, Webb becomes the faint thing. It becomes an object that would require another instrument, another act of curiosity, another being willing to look carefully into the dark. There is a pleasing symmetry in that. Every observatory is both an eye and an object. During its active life, we think mostly of what it sees. Later, if it survives, we may think of how it could be seen. Hubble might someday be studied as an artifact of early space astronomy. Voyager might be found, though the odds are tiny. Webb, drifting or fragmented, might become a target of future archaeology. The observer becomes observed. The instrument becomes evidence. The machine that read the universe becomes a line in the universe's own record. Still, at 1 trillion years, the odds favour transformation rather than preservation. A pristine Webb in a pristine orbit around a familiar sun is not a realistic picture. A silent relic, if it exists, would be damaged, altered, displaced, or reduced. It might be one fragment among ancient debris. It might be atoms in the old sun's white dwarf atmosphere. It might be dust spread through a darkened system. It might be interstellar material after ejection. It might be memory in an archive orbiting a red dwarf far from the solar system. The phrase, a silent relic, may therefore describe not one object, but a category of possible remains. Silence can be physical, orbital, cultural, or all three. And yet, even imagining one surviving fragment is enough to connect the early universe Webb studied with the far future it enters. Webb saw galaxies from near the beginning of cosmic history, when the universe was young and light was first assembling into structures we can recognize. Then, across the other direction of time, the telescope's own material may travel into an era when galaxies are older, dimmer, and quieter. It belongs to a beautiful middle moment, built by beings in a mature but still living solar system, looking backward toward cosmic dawn, then carried forward toward cosmic evening. Not the final darkness, not yet, but a later, slower age. That middle position is something we share with it. We live after the universe's beginning and before its deepest future. We live while galaxies still shine brightly, while the sun is still stable, while Earth is still alive, while the Milky Way is still recognizable, while stars are still being born. Webb is one of our ways of noticing that. It tells us that the universe has a past, and by thinking about Webb itself, we remember that everything in the universe also has a future. Even the instruments we use to study time are inside time, so if we place Webb in the galaxy of 1 trillion years from now, we should not picture it as a heroic spacecraft still gleaming untouched, holding its mirror toward the ancient dark with perfect dignity. That is a comforting image, but too tidy. Better to picture a range of possibilities scattered through an old galaxy. A small fragment near a white dwarf. A faint piece of reflective material tumbling slowly in a cold orbit. A few atoms inside an old stellar remnant. A trail of dust no one recognizes. A file in an archive, if archives have survived. A story told by some future mind about the age when Earth was young enough to build telescopes and old enough to wonder where they would go. From that far perspective, Webb's silence is not emptiness. It is the natural quiet of a completed mission carried into a much larger universe. It no longer sends data, but the fact that it once did remains part of the chain of events that led from curiosity to knowledge. The galaxy may change beyond recognition. The stars may fade into long-lived red embers and cooling remnants. The sun may shrink into a white dwarf. The Earth may vanish or become a dead world. But somewhere in that enormous transformation, Webb's material, memory or influence may still be present in some altered form, and now the question narrows toward its final shape. Not whether Webb will still work, because it will not. Not whether the Milky Way will remain the same, because it will not. Not whether the Sun and Earth will keep their familiar roles, because they will not. The last thing to ask is what all of this means when we stand here now, at the beginning of Webb's story, while it is still close enough to command and recent enough to remember. And so, after following James Webb from its quiet working place beyond the moon, through the strange balance around L2, through its future silence, its long drift around the Sun, the death of the familiar solar system, and the older galaxy that may one day carry its remains, we come back to a much smaller and gentler thought. Right now, Webb is still close enough for us to know. Not close in the way a mountain is close, or a city, or the moon glowing through a bedroom curtain, but close in the careful astronomical sense. Close enough for radio signals to cross the gap. Close enough for engineers to check its health. Close enough for scientists to ask it to turn toward a galaxy, a forming star, a cold planet, or a patch of darkness that may not be empty at all. Close enough that the light it gathers can still become an image on a screen here on Earth, where someone may look at it late at night and feel, just for a moment, that the universe has leaned nearer. 1 trillion years from now, that kind of closeness will almost certainly be gone. Webb will not be an active telescope then. It will not be carefully turning its mirror toward early galaxies. It will not be measuring starlight through the atmosphere of a distant world. It will not be waiting for commands from Earth, because Earth itself may be gone, or changed so deeply that the word home would need a very different meaning. The Sun will no longer be the warm yellow star we know. It will be a white dwarf, a cooling remnant, small and dense and faint compared with the star that once lit our days. The moon may no longer travel with Earth in the familiar way, and even if some trace of that old partnership remains, it will not be the moon of tides, calendars, quiet walks, and silver light on water. The solar system will have stretched and dimmed. The galaxy will have aged. The constellations we know will have lost their shapes long before. And Webb, if anything of it still exists, will be far from the shining observatory we imagine now. It may be a fragment, it may be dust, it may be a small piece of gold-coated mirror, scratched and darkened, moving around a dead sun. It may be a torn piece of shielding, if such a delicate thing could survive even a fraction of that time. It may have fallen into the sun's white dwarf remnant. It may have been scattered outward by a planet, disturbed by a passing star, or lost into interstellar space as a manufactured grain no one will ever find. It may exist only in records, if records survive, or it may exist in a quieter way, through the discoveries it made, through the knowledge that passed from one generation to another, even if the name James Webb eventually becomes unknown. That is the difficult part of deep time. It does not only stretch distance and age, it stretches identity. It asks when a telescope stops being a telescope, when a relic stops being recognizable, when memory becomes history, and when history becomes something too faint to recover. But perhaps the most important thing is not whether Webb lasts physically for 1 trillion years. It almost certainly will not last unchanged. Nothing made for spaceflight is built for that kind of duration. The mirror, the shield, the instruments, the structure, the electronics, all of it belongs to a mission measured in years and decades, not in the lifetimes of galaxies. Webb's greatness is not that it will remain whole forever. Its greatness is that it works now, in this narrow and precious window, while Earth is still alive, while the sun is still stable, while the sky still contains young stars and old galaxies, while there are people who can receive its data and ask what it means. A telescope does not need eternity to matter. It needs a clear purpose, a brief chance, and enough time to turn darkness into understanding. That is true of so much in science. A rocket launch lasts minutes. A mission may last years. A scientific paper may take months to write. A discovery may begin with a signal so faint it has to be checked, corrected, doubted, and checked again. But the result can change how we think about everything. Webb's images of distant galaxies are not only pictures, they are pieces of evidence from the young universe. Its measurements of exoplanet atmospheres are not only graphs, they are steps toward understanding what worlds can be. Its views of star-forming regions are not only beautiful clouds, they are records of matter becoming stars, disks, planets, and perhaps someday places where chemistry learns to be complicated. The telescope is temporary, but the questions it touches are old and wide. When Webb looks into deep space, it is also looking into deep time. This is one of those ideas that sounds almost too strange to be real, and yet it is one of the simplest facts of astronomy. Light takes time to travel. The farther away something is, the older the light we see from it. A galaxy billions of light years away is shown to us not as it is now, but as it was when the light began its journey. Webb's mirror catches photons that left their sources before Earth had humans, before dinosaurs, before plants, before the sun itself, depending on the source. Those photons travel across expansion, darkness, dust, gravity, and time, and then a few of them end their journey on a cold mirror beyond the moon. That alone is almost enough to sit with for a while. A particle of light can cross a universe, and a machine made on Earth can be waiting for it. And then we turn the thought around. Webb sees the past, but Webb also has a future. Every object does. Every tool, every stone, every star, every speck of dust. The telescope that studies ancient light is itself travelling into an age it will never understand. Its working life is a brief bright interval between two enormous silences. Before it was built, the universe existed for billions of years without it. After it falls silent, the universe will continue for times far beyond any mission timeline. That does not make Webb small in a dismissive way. It makes it precise. It belongs to a particular moment, and that moment is ours. There is something comforting in that, if we let it be comforting. We often think meaning must be permanent to be real. We want things to last. We want monuments to stand, names to be remembered, records to survive, machines to keep working. But the universe does not offer permanence easily. Stars change, planets change, galaxies merge, even atoms may be rearranged into forms we could never trace back. What the universe does offer is participation. For a while, we are here. For a while, Earth can build telescopes. For a while, a mirror can unfold in space and catch light from the first galaxies. For a while, people can look at that light and think, this is where we come from, or at least one part of the answer. Webb's last light, then, is not necessarily the last photon it ever collects. It is the last meaningful exchange between the telescope and the world that made it. One day, perhaps decades from launch, a final observation will be taken, though no one may know at that moment that it is final. A target will be chosen, Webb will point, the instruments will measure, data will be stored and sent, the signal will arrive at Earth. It may look ordinary at first, Just one more file among many, one more entry in the archive, one more planned observation in a long mission. Only later, after some failure, after some silence, after some attempt to recover contact, might people realise that this was the last new light Webb gave us. No dramatic announcement from the telescope itself. No farewell message, just the end of a stream that had been flowing quietly from beyond the moon. That final data may be used for years. It may be studied, reprocessed, compared, questioned, and cited. Someone may build a career partly from it. Someone may notice something in it that others missed. A future telescope may confirm or correct it. In that way, even the last observation would not really end when it arrives. It would enter the long human process of understanding, where information is never completely still. Webb's active voice will stop, but its archive will remain alive as long as minds continue to read it. And perhaps, somewhere very far ahead, if memory survives in some unexpected chain, Webb may be remembered not for where it ended up, but for what it allowed us to see while we were still young enough to be surprised. It may be remembered as one of the early instruments that helped humans understand that galaxies formed earlier and more richly than we expected, that planets around other stars have atmospheres worth studying, that star birth can be hidden behind dust and still revealed in infrared, that the universe is not only large but layered in time. Or maybe the details will be lost, and only the idea will remain, that there was once a telescope built by people on Earth, sent into cold space, to look for the oldest light it could find. If no memory survives, the story still happened. That matters. A fact does not become false because it is forgotten. Webb still launched. It still unfolded. It still cooled. It still looked. It still gathered light. It still sent data home. For a period in the life of the solar system, it was one of the finest tools our species had for understanding the universe beyond our ordinary senses. The universe did not need to remember it for it to be real. We remember it now, and now is where remembering always begins. So where will James Webb be in 1 trillion years? The honest answer is that we cannot know exactly. The future is too long, the object too small, the solar system too changeable, and the galaxy too restless. Webb may be dust around a white dwarf. It may be debris in a widened solar orbit. It may be material that fell into the old sun. It may be a fragment wandering between stars. It may be only data if preserved, or only influence if the data shaped knowledge that continued forward. It will not be the clean, golden observatory we know from mission images. It will not be a working telescope beyond the moon. It will be transformed, as all things are transformed by enough time. But if the exact location is uncertain, the larger answer is clear. Webb will be somewhere inside the consequences of the universe it studied. Its atoms will still belong to physics. Its discoveries will still belong to the chain of knowledge, if that chain survives. Its brief working life will remain part of the history of this small planet's attempt to understand a much larger cosmos. 1 trillion years is too long for certainty, but not too long for wonder. And now, after travelling all the way to that distant future, we can come gently back to the room you're in. Back from the white dwarf sun, back from the changed galaxy, back from fragments, dust, and ancient orbits. Back to this moment, where Webb is not yet a relic in deep time, but a real telescope still close enough to be part of our present story. Somewhere beyond the moon, it is cold and quiet. Its shield faces the warmth. Its mirror faces the dark. It does not know that we are imagining its trillion-year future. It does not know that we find meaning in its silence or comfort in its mission. It simply works as it was built to work, one observation at a time. Maybe that is enough for tonight. Maybe the thought of Webb in 1 trillion years is not meant to give us a perfect answer, but to loosen our grip on the idea that everything important must last forever. A telescope can be temporary and still change the way a species sees. A planet can be temporary and still be home. A star can be temporary and still warm oceans for billions of years. A moment can be temporary and still matter, especially when you're inside it. So if you're listening late at night, with the world around you becoming quiet, you can let Webb's journey settle into something simple. Far away, beyond the moon, a telescope made on Earth is looking into old light. Far ahead, in a future too large to picture clearly, whatever remains of it will be carried by gravity, changed by time, and folded into the long history of the matter. Between those 2 points is the part we get to know. The active years, the discoveries, the images, the questions. The strange comfort of realizing that even a machine can have a life story when it travels through the universe. And perhaps that is where we can leave it softly. Not with Webb shining forever, because it will not. Not with the sun staying young, because it cannot. Not with Earth unchanged, because nothing is. But with the understanding that for a little while, during a calm and lucky interval in the life of a star, a world built a telescope and sent it into the dark. It caught ancient light. It helped us see farther than before, and then, like everything else, it continued into time. Sleep well, fellow traveller, wherever you are on Earth tonight, and whatever time it is in your small corner of the planet. The universe is old, the future is wide, and somewhere beyond the moon, James Webb is still listening to light that has been travelling longer than any dream.